Okay, great. Okay, so this talk is going to be, and like I said to the people in the room that like this talk's gonna be pretty different from what you all are used to. So if you have questions, feel free to ask them. We have the time to go through this, step by step. So this talk is going to be about AI for games, and I want to start with this XKCD comic that came out in 2012 on various games and the difficulties of them for AI. So there's four categories: games that are completely solved by AI, games where computers can still beat top humans, games where computers can beat top humans, games where computers still lose to top humans, and then games where computers may never outplay top humans. And so you have, like, for example, in the games that are solved, Connect 4, computers can beat top humans. You have things like Counter-Strike. This came out in 2012, and so Jeopardy is right over the line because IBM made Watson in 2011. And then computers still lose to top humans has four games: StarCraft, Poker, Go, and Arima. So in 2015, Arima was this like modification of chess that was designed to be very difficult for AIs to play. But actually in 2015, David Wu, my collaborator at FAIR, actually made the first AI to beat top humans in Arima. In 2016, famously, there was AlphaGo from DeepMind, which beat top humans. My own work, so my PhD research was focused on making AIs that could play poker. And so we succeeded in 2017 for 2-player poker, and we followed this up in 2019 with 6-player poker. And also in 2019, DeepMind created AlphaStar, which didn't quite beat top humans in StarCraft, but reached Grandmaster level. And at this point, this could probably be superhuman. So I think this shows two things. First of all, it shows the incredible amount of progress that has been made in AI over the past decade. Again, this comic came out in 2012, and within 7 years, all of these games were conquered by AI. But it also raises the question about what's next. And this has been a question that actually a lot of AI researchers have been thinking about. And there's been various proposals. So in 2019, DeepMind put out a paper about Hanabi, saying this is the new frontier for AI research, that it's this grand challenge because Hanabi is a cooperative game. But actually that same year, my collaborators and I put out a paper showing that we could reach superhuman performance in self-play Hanabi, where a bot is playing with another copy of a bot. And we actually just finished up human experiments about a month ago, showing that we can also beat top humans when playing with just like actual humans in this game. And so Hanabi, it turns out, is not terribly difficult for AI. Mahjong, again, people like were pointing to this, but 2020, MSR Asia put out a paper showing superhuman performance in Mahjong. I've even heard proposals about first-person shooters, Counter-Strike being one example, but actually bots have been superhuman in Counter-Strike since 1999. And that's just because, if you're playing a first-person shooter game, all you have to do is just be able to like click the mouse really accurately on, the pixel of the person's head, and then you're going to win the game. You don't have to be very intelligent about it. And I think that's actually a good example of like just looking at the complexity of a game is not like the state space and action space of the game is not sufficient for really measuring the challenge of AI. Counter-Strike is a 3D game with a continuous action space, continuous state space, partially observable, all sorts of like really difficult challenges, seemingly, but it's actually really easy for an AI to play. And so I think what this shows is that, people have not been ambitious enough with setting a goal for a new grand challenge for AI. Chess took decades for researchers to figure out. Go took decades as well. Poker took decades. And so we have to think a bit, broader, more ambitiously about what really is still difficult for AI.
I have a quick question.
Yep.
Out of curiosity, this Counter-Strike bot since 1999 thing, what information did the AIs have? Did they have like coordinates of the things that they're supposed to shoot, or did they didn't have just the pixels, right?
Yeah, but now they did the StarCraft bot. StarCraft bot didn't operate on pixels either.
Oh, okay, yeah. Fair.
Okay, so this leads me to diplomacy, and I want to suggest that diplomacy is such a game that's like truly absurdly difficult for an AI to play well. So diplomacy is a board game. It was actually created in the 50s. It was Henry Kissinger and JFK's favorite board game, and it's very different from pretty much all existing board games and all existing computer games because it really is focused on negotiation with the other players. It's focused on private natural language communication with other players. So Diplomacy is a board game. It's a 7-player game with, first of all, an extremely large action space. So you control one of the 7 powers of Europe right prior to World War I. And it's really supposed to simulate like the complex alliance structures going on before leading up to World War I. I should point out that there is a Russia power in this game. There is a Ukraine power in this game, Ukraine territory in this game, and obviously, we have to be sensitive about the current European situation. And this game is not intended to model present-day politics. It's takes place around 19. The game actually starts in 1900. It's supposed to simulate European politics 100 years ago. So you control one of these 7 powers, and you have a bunch of units. And on each turn, all the players simultaneously move each of their units to a neighboring territory, or support a movement to that territory, or just don't move. Now, what's key? There's a few things that are key about this game. One is that all the actions are done simultaneously. And the second thing that's really important is that support is really, really important. The only way that you can enter a territory is if you have more support going into that territory than the other side does. So to give you an example, let's say we have the purple power and the red power. So purple and red are both simultaneously write down their orders to move to Galicia. And so those are executed simultaneously, but since they're both going in there, it's a 1 versus 1, and so they bounce back and neither unit goes in. Now let's say the red player writes down, I'm going to move my unit in Budapest to Galicia, but I'm also going to have Vienna support that movement. So now it's a 2 versus 1, and so that unit from Budapest will actually move into Galicia. But what's really important here is that it doesn't have to be just your units that are supporting your other units moving. You could have, for example, the green player supporting the unit from Budapest into Galicia. And so that would go through. And so the way the game works is every turn before, you're going to write down the moves and they're all going to be executed simultaneously. But before that happens, everybody spends 15 minutes talking to other players in private, making all sorts of deals, making all sorts of requests. So, red goes to green and says, hey, could you please support me into Galicia this turn? And if you do that, I'll help you out next turn. This is all done in natural language. There's nobody is like bound to what they say. And so you can make all sorts of promises, but there's no mechanism in like forcing you to follow through with that. And so, green can go to red and say like, yes, I'll support you into Galicia, but then they can go to purple and say, no, actually, I'm going to support you into Galicia. And so when the moves are actually written down and executed, you don't actually know what's going to happen. Have any of you seen the TV show Survivor? Yeah, a few. It's a lot like that, like people are making all sorts of promises, but then when the votes actually happen, you don't really know who's getting voted off the island. And so this like negotiation phase is really what the game is all about. It's about trying to get people to work with you, build trust, convince them that you are trustworthy, and then at the right time, possibly lying to them. And because of this deception aspect, Diplomacy has a reputation as the game that ruins friendships. And I can attest that this is true. It's really difficult. These games last for like 6 hours, and it's really difficult to be in a really solid alliance with somebody for like 4 hours of that game, and then suddenly out of the blue they like totally stab you, and you're just like wrecked for the rest of the game. And yeah, so it has this reputation as like the evil board game that like, and again, like most people don't enjoy playing Diplomacy because it's just like really, and honestly, I don't even enjoy playing it that much because it's just really difficult to play. But I think other players, if you talk to professional or like top Diplomacy players, they see it differently. They say Diplomacy isn't about lying and deception. It's really about building trust in an environment that encourages you to not trust anyone. And I think this is really important. I mean, it's really easy to, play a cooperative game and have an AI that never lies to you. But what's really hard is, getting an AI to convince you that it's trustworthy and that it's worth working with in a game where there is this incentive, constant incentive to backstab and betray. And so I think this is really what makes diplomacy interesting. It's about building trust. It's about understanding that there is this risk of deception, that this person might think I'm lying, or this person might be lying to me, and I have to overcome that barrier. Um, and I think building an AI that is capable of doing that, is able to understand that this person might be lying to me because it is in their strategic interest to do so on this turn, and that this person should be concerned about me lying to them because I have a strategic interest in betraying them this turn, and I have to overcome that, and to be able to negotiate good deals and understand that like this person has alternative offers, that they could work with these other powers instead, and I have to undercut that. That is, I think, a real challenge for AI. That is far beyond what is possible today, even with all the progress that's been made in game playing and natural language. And so I really see this as a true grand challenge for AI. Yeah, so I think this is obviously not something that's going to be doable in 1 year or 2 years or maybe even 5 years. But again, if you look back at Go and chess and poker, those took decades for AI researchers to figure out. And I think that the field needs a similarly ambitious goal today. All right, so that's the motivation for diplomacy. Any questions about that so far? Yep.
Just have I don't know, maybe a bit random question, but when you train these AIs with self-play, how like I'm thinking about how it actually works then with natural language. How do you ensure that they are not like start communicating like something that's not really, I don't know, human interpretable?
Yeah, so that's actually like one of the main focuses of this talk, that self-play does not work in this game. Yeah. And yeah, I'll show that even without natural language, it ends up being a huge problem. Like even if you ignore the natural language part. Okay. Okay, so that's the like grand vision of where this research is headed. Eventually we want to make an AI that can play this game in natural language with real humans and ideally beat them. Obviously, it's a very ambitious goal, and so what we've been working on so far has been a more realistic challenge that's achievable in the short term, which is gunboat diplomacy. Gunboat diplomacy is a version of the game where you do not talk to the other players. You can still signal things through your moves. So for example, if you want to support somebody next turn, you can support them this turn and say like, kind of like implicitly like, I'm going to do this. It kind of like implies that you're going to do this action again, this support action again. So this is actually a very popular version of the game that's played by humans. It goes much faster, which is nice. Coordination and alliances are still a big factor. And so we thought this would be a good starting point for making an AI. And actually other research labs have been working on this version of the game as well for now. And what's really interesting, we actually showed this in a paper. Self-play is not enough to make an AI that's strong in gunboat diplomacy or superhuman in gunboat diplomacy. What I mean by self-play is that if you look at all of the previous AIs for games, chess, Go, poker, they all work basically under the same principle, that they don't really care how humans play the game. What they're going to do is have the bot from scratch play against itself for trillions of games. And then along the way, it's going to gradually improve and get better and better, and then eventually arrive at the mini-max solution for the game, the unbeatable strategy that guarantees that it will be able to beat any human alive. And it turns out this only works in theory for 2-player zero-sum games. And it was an open question of whether it's true for just theory or also in practice. So for example, when I worked on 6-player poker, we also did this self-play thing where we just like ignored how humans play and just had the bot play against itself for trillions of games, and it ended up beating top humans. And so there was this question of like, how far can self-play get you? Well, it turns out self-play does not work in diplomacy, even gunboat diplomacy. Now, to give you some intuition about, yeah, sorry, go ahead.
Can you explain why there's like such a difference between poker, where you also have imperfect information and you also have like this kind of like coordination going on? Maybe
yeah. So my hypothesis is that poker is a very adversarial game, and so there's no cooperation or coordination going on with the other players. It's really hard to do that. And so if you have a very adversarial game, then you can just do self-play and everything will work out fine. But if you have games that involve cooperation, then you actually can't just rely on self-play. Now, to give you some intuition as to why, imagine you have, you want to make a self-driving car. And so the way you decide to train this self-driving car is by having it drive with other self-driving cars on the road. Like there's no human data. It's just learning from scratch how to drive with other self-driving cars on the road. And you create this simulation and they, train for trillions of hours and they get really good. The one problem is that they end up driving on the left side of the road. Now that's a totally reasonable solution, right? You can imagine a world where all the cars drive on the left side of the road. In fact, that's actually what happens in some countries. And it works out really well. There's no accidents. Everybody gets to the places they're trying to go. The problem is that if you then stick that car on the road with real humans in America, it's going to crash. And so that's an example where self-play, what's going on is that self-play is arriving at an equilibrium that is totally reasonable, but is different from the equilibrium that humans play, or could be different from the equilibrium that humans play. Now, this is not an issue in two-player zero-sum games because two-player zero-sum games have a very special property where all the equilibria are interchangeable. You can take one player solution from one equilibrium and a different player solution from a different equilibrium, stick them together, and that is another equilibrium. A more technical way of saying it is that the space of equilibria is convex. That is only true in theory in two-player zero-sum games and some other special classes, but not true in general. Yep.
Yeah, just to make sure what the goal in diplomacy or in gun is, there's just one winner, right?
That's a great question. So it's a bit complicated actually. You can have draws, and then so there's you can imagine there's a pie, and the pie gets divided depending on how people draw a vote, and so you could split the pie between the surviving players. But it's still it's a zero-sum game in that there's a fixed size of the pie. But because there are 7 players, if you look at any pair of players, it's a cooperative game from their perspective because the two of them can work together to both get bigger shares of the pie.
So there could be groups that win, not just one person that wins.
Yes, there could be. Yeah.
So it's you have to check for every 2 different groups in the pool of players, and
not just 2. There could be 3 or 4.
Yeah, more. Yeah. I mean,
every subset. Yes.
Any 2 subsets could be a zero-sum between these 2 subsets in the overall.
Yeah, I would say so. This is I think a thing that trips up a few people. Any general sum game, any n-player general sum game can be converted into an n+1 player zero-sum game by just adding an extra player that has no decisions and gets the negative payoff of everybody else. So what that means is that just because the game is zero-sum or fixed sum doesn't actually mean doesn't mean anything if there's more than 2 players, because it still has all the complexity of a general sum game in it. Because any subset of the players, from their perspective, it's a general sum game.
Yeah, I was just wondering because if you would have chosen at the start of the game who is with who, who are the teams?
Oh, sure. If you're setting the teams up front, then yeah, it's basically the same thing as a 2-player zero-sum game. But I think that a lot of the complexity from diplomacy comes from you don't have preset teams and you have to establish those as you go, and they can shift as the game progresses. Yes?
What's the definition of an equilibrium in this context?
That's a great question. Yeah. So I come from a game theory background, and so again, this is very, very different world from what you're all used to and from what I'm used to. So an equilibrium, a Nash equilibrium is a strategy, as a policy for each player, where no player has an incentive to deviate from that policy. So you can think of in rock, paper, scissors, the equilibrium is to randomly choose rock, paper, and scissors with 1/3 probability each. Because if you're doing that, then neither player can improve by deviating to a different policy. And so another equilibrium with self-driving, with driving on the road, for example, is everybody drives on the right side of the road. Because if everybody's driving on the right side of the road, you don't have any reason to switch to driving on the left side of the road. But there's multiple equilibria. There could be multiple equilibria. So you could drive on the left side of the road, you could drive on the right side of the road. But once everybody's doing one equilibrium, it doesn't really make sense for you to shift to a different one. At least unilaterally shift. Okay. So going back to my point, we actually show this in a paper where we trained a gunboat bot through self-play, and it didn't end up doing well against human or humans. And so what this shows is that it's not just enough to find one equilibrium. What we really need to do is understand how humans play the game. We need to understand the human equilibrium, and not just the human equilibrium, because humans might not be playing an equilibrium, but we have to be able to do well when playing with actual humans. And so that means modeling the fact that humans are not always rational, for example. Like one really interesting thing that we found with our self-play bot is that, if somebody backstabs you in diplomacy, it's not really rational for you to just like give up and do everything you can to get revenge on the person that stabbed you. Like that's a very human thing to do, and actually humans do that. If you like backstab them, they'll just flip out and spend the rest of the game trying to ruin you. Bots in self-play don't really learn that, and so when you stick them in a game with actual humans, they're backstabbing and they think like, yeah, this is no big deal. Like, of course, there's a free center, I'm going to take it from you, and like we can still work together after this. But then of course the humans flip out and ruin the bot, and so the bot doesn't end up doing well. And so if you really want to do well with actual humans in the game, you have to be able to understand this aspect of human behavior and be able to work around it. Yeah, so this is, I think, one of the really interesting challenges, not just of gunboat diplomacy, but also of the full-scale diplomacy. And this is a challenge that we have not seen in prior game AIs. And this poses a really big challenge, because if you think about why AI works so well in games like Go and chess and poker, it's because you can collect basically infinite data. You have the bot play against itself, trillions of games. You can collect infinite data and then learn how to play optimally given that data set. But when you need to understand how actual humans play the game, you have to collect infinite data of how actual humans play the game, and you can't do that. And so how do we cope with the fact that we don't have infinite data of how humans play this game? And that's kind of what this talk will lead up to, that we find a way to combine self-play with human data, basically regularize the self-play so that it stays close to the human policy and is able to then understand and fill in the gaps of how humans play and get better still. And so that's what I mean by this part about assuming some rationality. Basically, we do self-play, which assumes some rationality on the parts of the agents, but we regularize that towards the human policy so that we don't like just deviate too far from the human equilibrium. Okay, so I want to talk a little bit about prior work for diplomacy. This has actually been a long-standing challenge problem in the field of AI. It did not get much attention in the past because it was just so absurdly difficult. I mean, you can imagine like the thought of trying to get an AI to negotiate in natural language back in the 80s was just like unthinkable. But researchers still worked on the game. They took relatively heuristic approaches. And there were publications in the 80s, 90s, 2000s. They were actually like, surprisingly good for gunboat, but still, below human level. There was a big shift in the research starting in 2019. So in 2019, Mila put out a paper on AI for gunboat diplomacy, where they trained a neural net on human data of the game. So they collected a data set of about 5 million state action pairs from this website, webdiplomacy.net. Where people play diplomacy online. They just did supervised imitation learning, made a bot from that called DipNet, and it was actually like reasonably good. I would say it performed at about an average human level, but it's very exploitable. So the way they got it to play at an average human level is by setting the temperature very low, which means that it's very predictable because it's just doing like the most common thing. And so it'll actually like very frequently play the same move over and over again. And in a game with simultaneous moves where you have to be unpredictable, sometimes it's actually quite easy to beat if you catch what it's doing. But that's nevertheless very good starting points. And this really launched the research, the modern research direction. Yeah.
Why do you have to keep the temperature low?
In theory, you don't. If you have enough data, you don't. But if you have enough model capacity, you don't. But in practice, because there is just like not enough data and not enough model capacity, it will put a lot of low probability on very bad actions. And so basically the action that has the highest probability, like you can imagine in an equilibrium, you're going to have a mixed policy where you're going to be putting like some probability on various actions because you don't want to be too predictable. Now, some actions are going to have zero probability because they're just bad. Some actions are going to have low probability. Some actions are going to have high probability. But to be clear, any action that has positive probability is equally good. Like it wouldn't make sense for an action with low probability in theory to have worse value than an action with high probability, because if that were the case, then you would just put more mass on the high probability action. But what ends up happening in practice is that the neural net has error. It kind of misestimates the expected values. And so the actions that have the highest probability, it's most confident about being good actions. And so if you just like have it always play the action that has the highest probability, then that's the action that's most likely to be a reasonable action. And so we'll end up doing better in practice. The problem is that then you become very predictable. And so if the other person, it's kind of like in rock, paper, scissors, if you're just like always throwing rock, like if the other person doesn't adapt to you, that's a totally reasonable thing to do. But if they catch on to what you're doing, then they can start throwing paper and totally destroy you. Does that make sense?
Yeah, I was just thinking like maybe during training you can keep the temperature low, but at like when you're actually like playing against humans, maybe to add like randomness.
Well, so right now in this, there's no reinforcement learning. There's no like self-play going on. It's just pure imitation learning on human data.
Okay.
Okay, so this was followed up with work from DeepMind in 2020, combining supervised learning with reinforcement learning. And so the idea here is that they initialize the policy with the supervised learning, and then they do policy iteration for one player each iteration, playing against the opponent's average policy. This is equivalent to fictitious play, which I won't go into. Basically, this is a reinforcement learning algorithm on top of initialized from the imitation learning policy. Now, diplomacy is a 7-player game, which means that if you stick one bot into a game with 6 other bots, you should expect to, if they're equally strong, you should expect to win 1/7 of the time, or 14.3% of the time. If you take one of these RL agents from DeepMind and stick it into a game with 6 DipNets, that's Mila's pure imitation learning bot, the RL agent wins 20% of the time. So that's since that's higher than 14.3%, that means that it's doing better than DipNet. And one DipNet playing against 6 RL agents only scores 0.8%. So pretty convincing evidence that the RL bot is beating DipNet and is better than DipNet there. Yes.
So maybe you're going to do that, but if you're not, then maybe the question is a good one. Can you give like an overview of what the state space and the action spaces look like? Or like, is that an integral thing that you need to sort of define well, or does that like immediately come out of the game? Like that's how you have to write it?
Yes. I think I'll get to that a little bit later. It ends up not. Yeah, I think I have a talk about it a little bit. Yeah. Yes.
Maybe you're going to say this, but how does this agent do against actual human players? Because this doesn't actually say anything about.
Yes, that's a great question. So they actually didn't do those experiments. I did play against DipNet, so the Mila bot that was just pure imitation learning, and I think that one is fair to say it's like average human level performance. This one, I've never played against it. They never did any human experiments, so it's really hard to say how it actually performs. My guess is that it performs better than the previous bot. So I would say like still not strong human level, but probably like a little bit stronger than the DipNet agent, but nobody's tested that.
Because just this gives evidence that maybe it could exploit stuff in DeepNet and not actually.
Yes, that's fair. And this is one of the concerns. They did play against a different bot as well, and they found that it did better against that bot than DipNet did. So there is like some evidence that it's not just exploiting DipNet, but yeah, it's true that they ideally would do human experiments, but did not. Okay, so now I want to get to our work, which takes a question.
So I had a question about like what is kind of the input that all of these agents see? Is it similar to like how like a human would see the game, or is it?
Yeah, so the input is basically the board states, and then it really depends on the bot. Like in theory, you can see all the previous actions that have occurred in the game. So you can see like where all the units have moved on every single turn, and your units and the other players' units. The board is fully observable. So the only imperfect information comes from the fact that like you're doing all of your actions simultaneously. And so on the same turn that you're doing your actions, you don't know what the other players are doing, which means that you have to, just like in rock, paper, scissors, you don't know what the other person is doing the same time that you're acting. And so you have to mix. In diplomacy also, you want to be a little unpredictable and be able to mix. But the board state, the history is fully observable.
Okay. So like they have access to like all of the moves that all of the players have made.
Yes. Yeah. Okay. So this leads to our work. We take a slightly different approach. We don't actually do reinforcement learning in this bot, our 2021 bot. Instead, we did supervised learning plus equilibrium search. Now, the idea here is that we train a value function from the human data. So the value function says, given the board state and the history of actions from all the players, what is the expected value of each player right now? Like, again, there's a pi of summing up to 1. How does it look like that pi is going to be divided between the 7 players? So that value function comes purely through supervised learning from the human data. And then on each turn, we view the game as like basically what we call a sub game. You can kind of view it as like a mini game where we say like after this turn, imagine that the game ends. Once everybody submits their moves, we resolve it and see what the new board state is, and then we say the game is over, and we just use the value function that we've trained to divide the pie. And so that game is much smaller. In fact, it's small enough that we can represent it tabularly, and then we solve that much smaller game on each turn. Yes?
Sorry, this is a really basic question. Is there a time limit on your turn? If everyone has to move simultaneously, how do you determine how long before they make that?
That's a great question. So there's different time controls. If you're playing a live game, it's usually once every 5 minutes. When there's natural language going on, it's usually once every 15 or 20 minutes. And then when people play online and they actually like message people back and forth, turns are 24 hours. And so if turns are 24 hours, and actually we ended up doing human experiments where we played these 24-hour turn games, and so they can go on for like 1 or 2 months. It's a very long game. Yes, you can imagine there's a frustration of like working with somebody for a month and a half, and then they stab you, and yeah, very hard game to play. Okay, so the way we do this, yeah, question?
I'm not like really familiar with like reinforcement learning, like nomenclature. So what does the value function tell us?
The value function says, like if you're playing Go, for example, you look at the board state where all the pieces are, and you say like, who do you think is going to win? Like, give me a probability estimate of who you think is going to win. So that's like the value function. And in diplomacy, we're looking at the board state. We're looking at where all the units are, what all the actions have been up to this point. And we're saying, given this, can a neural net predict who is going to win this game, or who is going to, how the points are going to be divided between the players if there's a draw. And that's the value function. Does that make sense?
And then how do you use this to construct a matrix game? I didn't get that part.
Yeah, so you can imagine like imagine we're working with like a 2-player version of diplomacy right now, which there actually is a variant that's 2-player. And so we say like, look, we got this red player and this blue player, and the red player has all these different actions that they can take, and the blue player has all these different actions that they can take. And for each pair of actions, we're going to end up in some new board state. And that board state, we can plug into the value function and get an estimate of how each player is going to do at the end. And so we use that to construct this matrix. And you can kind of think of this matrix as like a very large form of rock, paper, scissors, where like simultaneously each player is going to choose an action, and then we see what the outcome is. They each get a payoff depending on the pair of actions that were chosen. And then, yeah, and that's it. And so the players have an incentive to be unpredictable, just like in rock, paper, scissors. So there's going to be some policy that's a distribution over these actions for each player.
Why do we have only 2 players in this setting? Like,
in this, I'm just trying to like explain this intuitively. In the actual version, we have 7 players, and so it's a 7-dimensional tensor. It's not actually a 2-dimensional matrix. Yeah.
Why didn't the history of action and not just the current state of the model?
That's a great question. So if it's a 2-player zero-sum game, like chess and Go, you just need the board state. But because it's a 7-player game, you have to understand if somebody is going to do dumb things in the future. That's actually really important. Like, you don't want to ally with somebody that's going to be doing really dumb things and is just going to like stab you for no reason. And that's actually a pretty important aspect of the game. And so if you don't look at the previous moves, you're not going to understand who's good, who's bad, who's attacking you, who's not attacking you. So you need that information. Like in chess, it doesn't really matter if the person you're playing against is dumb, because you're going to beat them anyway. But in diplomacy, it's actually pretty important, because you don't just want to you want to choose who to ally with and who to cooperate with as well. So actually what we do in practice, we only look at the previous move. We don't look at the entire move history. We actually ran a bunch of experiments to see if looking farther back increases performance, and we found that was not the case. For whatever reason, we don't have enough data, we don't have enough model capacity. Looking farther back than just one move didn't help us. So we look at the current board state and the previous move that everybody made, but not farther back than that. Yes?
I guess it's kind of related to what was asked now. The value isn't just, so I guess you do need to weight different actions from different people, but the value of the state is just how much area you have on the board, right? Like how many, or is it?
Well, it's not just like in Go, it's not about how much area you have right now, it's how much area you're going to end up with.
Yeah.
And so like if you have a big area of the board, but everybody is teaming up against you and is going to attack you simultaneously, then it's not looking too good for you long term. So really the value function is predicting where you're going to be at the end of the game, not just where you are right now.
So then the network is predicting the finite horizon like reward.
It's trying to predict the terminal reward at the end of the game.
Yeah, that's
fair. Yep. Okay. So yeah, this is the approach we took. We train this value function based on imitation learning of human data, and then we construct on every single turn of the game. We construct this tensor game and solve it tabularly, and then that gives us a policy to play for the current turn, and then we just sample from that policy. Yes?
But you would have to solve this game at every single turn. Right?
Yes, we solve it at every single turn. And so, it takes a bit of time. It takes like, when we first did this, it was taking like an hour. And so this is not looking too good for us, because we wanted to play like, 5-minute games. We have it down now where we can do it in like 30 seconds, even less.
Okay.
Yeah.
Is it not possible to have like the game, like the state also as a parameter to like this function? So
the state, you don't really need. So if you think about, we just need the tensor. We just need the matrix value, the value matrix. That's the only thing that's really important here, because if we can get the values down, we can just solve it. But the state does determine the values. So the value function takes as input the state. Okay, so Nash equilibrium, we kind of talked about this already, but like what we're trying to do here is compute a Nash equilibrium. So when I say like we solve this matrix game to try to come up with a policy, what we're doing is like essentially trying to compute a Nash equilibrium. Now, I should really attach an asterisk to that, because we're not actually computing a Nash equilibrium, and in theory, we can't in polynomial time. But in practice, that ends up being like what we're approximately doing. So a Nash equilibrium is a set of strategies or policies in which no player can improve by deviating to a different policy. And in two-player zero-sum games, playing a Nash equilibrium ensures that you will not lose an expectation no matter what your opponent does. So we measure something called exploitability, which is how much we'd lose to a best response, to a worst-case adversary who's best responding to us. So to give you some intuition, in rock, paper, scissors, if we throw a rock on every single turn, then the best response against us is to throw paper on every single turn. And so our exploitability is 1, because we're losing 1 point on every single turn. Now, we could try to be tricky. We could say we're going to throw rock on the first 2 rounds. And then if the other player throws paper on those 2 rounds, then we end up throwing scissors on the 3rd round. But in this case, our exploitability is also 1, because the opponent could just best respond to us by throwing paper on the first 2 rounds and then rock on the 3rd round. So our exploitability is still 1. Now you might say, well, this is unfair. We're kind of like assuming that the opponent knows our policy. And indeed, that is the case. The critical assumption that we're making is that our strategy, which is just another word for policy, our policy is common knowledge, but the outcome of random processes are not common knowledge. And the motivation for this is that if somebody is able to play against our bot for long enough, eventually they're going to find out what the weaknesses are. They're going to find out those little patterns, those little tricks, and be able to exploit it. So we want to do well even when an opponent has played with our bot for, you know, a million games. And so the way we get around this is by mixing. We have a mixed policy. If we randomly choose between rock, paper, and scissors with 1/3 probability each, then it doesn't matter what the opponent does, our exploitability is 0. Now, one thing I should point out is that in rock, paper, scissors, if you just do this, you know, 1/3, 1/3, 1/3 thing, you're going to be unexploitable, but you're not going to end up winning an expectation either. Now, that is true in rock, paper, scissors, but when you go to more complex games like diplomacy, or it's really like in poker, because this is what the approach that we took in poker, we try to approximate the Nash equilibrium. We find that the other player ends up making mistakes. So there are actions that shouldn't be played with any probability. The opponents play those actions because they're not perfect, and we end up winning because they made mistakes. And so that's the intuition behind this like Nash equilibrium, this like equilibrium approach to game playing. And in fact, this is the approach that we took when I was making poker AIs. It worked really well, and this is actually the approach that professional poker players take as well. In fact, there's a strategy guide for poker that says poker is simple. As your opponents make mistakes, you profit. Okay, so this is what we're trying to compute. We're trying to compute an equilibrium. How do we do it? Well, I'm going to introduce 2 techniques. The first one is fictitious play, and this is really, I think, the most intuitive technique that you can come up with. Basically, it's an iterative algorithm, and on every iteration, both players best respond to what the other players have done on the previous iterations. So imagine you're doing rock, paper, scissors. You have 2 players. On the first iteration, they both throw rock. On the second iteration, they best respond to the average of all the previous iterations. Now, since the previous iteration was rock, the best response to throwing rock is to throw paper. So on iteration 2, they both throw paper, and now their policies are half rock, half paper. On iteration 3, they best respond to that policy, which would be to throw paper. So now their policy is 1/3 rock, 2/3 paper. On the fourth iteration, they best respond to the policy shown there, the 1/3 rock, 2/3 paper, and the best response is to throw scissors. So they throw scissors, and now their policy is 1/4 rock, 2/4 paper, 1/4 scissors. And if you keep doing this, eventually it's going to converge to 1/3, 1/3, 1/3. This is called fictitious play, very popular algorithm. It's actually quite slow though. And so there's an alternative that's much faster, which is called regret matching. This is the algorithm that we used to train poker AIs, and this is the approach. This is the algorithm that we also use for diplomacy AIs. Now, fictitious play is always picking a best response to the opponent's average policy. Regret matching is different in that it's basically picking a soft best response to the opponent's average. So there's different ways you can do regret minimization, but this is the one that we use. I won't go into the details of it, but basically you can think of it as like a soft max instead of just a pure best response. Yep.
In diplomacy, we only cared about what the final area we have, and now it seems that we're looking at the like intermediate expected increases scenario we can get.
Yes. So okay, the reason for that is because the value matrix is already accounting for. So the entries in the value matrix are the prediction of the value that you'll end up with at the end of the game. And so when you're solving this matrix game, you're not trying to find the policy that's going to get you the maximum territory this turn. What you're doing is finding the policy that will maximize your territory at the end of the game, because that's already accounted for in the value matrix. It's like in Go or chess, when you're computing the optimal policy for the next 5 moves, the value function that you're using is trained to predict the end game result. So it's not like it's just trying to like maximize your points in the short term. That is accounted for in the value function that you're trained. Okay, so the way we solve this tensor is by running regret matching. Now, this doesn't actually converge to a Nash equilibrium in theory, but what we find in practice is that it actually does get quite close to a Nash equilibrium. So this is a plot. On the x-axis, we have number of iterations of regret matching that we've done. Y-axis, we have exploitability, which is how far we are from a Nash equilibrium. And the dotted lines, the dashed lines, are if we don't do any search, if we don't do any equilibrium search, if we just play the policy net that was trained through imitation learning. And for various temperatures, you can see that there's different levels of exploitability. But if you do regret matching, exploitability drops by about an order of magnitude. And I think actually this result by itself is pretty impressive because a lot of people were very dismissive of regret matching because it doesn't converge to Nash equilibrium in theory outside of two-player zero-sum games. But what we find empirically is that it actually does quite well for approximating them, even outside of two-player zero-sum games. Now, there is one more challenge that I want to talk about, which is that we have a very, very large action space. So I said on each turn, you're controlling between like 3 and 10 units, and each of those units can move to like 10 different territories neighboring them, or they can support another unit into a territory. So like the action space is just something like 10 to the 50 on every single turn. Now, obviously, you can't construct a tensor where or even a two-player zero-sum game. You can't construct a matrix game where each player is choosing between 10 to the 50 different actions. And so what we do is we sample from the policy net. So we've trained a policy net on the human data, and we see what are the 20 or 50 most common actions from this policy net. We sample from it, and then we put those actions into the matrix game. So we're only considering a small subset of the actions that are actually possible, but the hope is that the human data is reasonably good enough that it can at least, the optimal, the best actions that you could play are somewhere in the top 50 of what humans tend to play. Yes?
Right. The actions, like the movements of each one of the units to another place?
Oh, sorry. Yes, that's a good question. So what I mean by action, so I use order and action to distinguish between these two things. So order is moving one single unit to a neighboring territory or supporting or holding. And I use action to refer to all of the orders for all of your units. So the action, you choose one action on each turn, and you choose an order for each unit.
And all this together is like.
So when I talk about like the entries in this matrix, the rows in this matrix, these are referring to actions. So each action is like a combination of orders for all your units. Okay, so how does this actually do? Well, there were 3 types of evaluations that we did. One is anonymous games against humans on webdiplomacy.net. One is performance against prior bots, and then the other is repeated games against expert humans. So first, evaluation against humans on webdiplomacy.net. The bot scored 26.6%. Again, if you are equally strong as humans, you're going to score 14.3% because that's 1/7. The bot is almost double that. And in fact, if you look at the ranking of the bot, it was in the top 2% of human players on the site. So very good, but not superhuman. We also played it against DipNet. DipNet, again, is that bot trained by Mila purely through supervised learning on human data. And so we have search bots, which is what we call our bot. It scores, if you take one search bot and play it against 6 DipNets, it scores 51%. If you take one DipNet and play it against 6 search bots, DipNet only scores 0.7%. So we're much stronger than the prior bots. And finally, playing against expert humans. So here we invited 2 very strong players. In fact, the previous world champion and the second place finisher of the world championship to play repeated games against the bot, and knowing that it's a bot. So they play against 6 copies of the bot. If we had them do this experiment against DipNet, which once again is the supervised learning policy from Mila, trained on human data, and there they were able to win 39% of the time, which again, if they're tying, it would be 14.3%. We had them play against our pure supervised learning bot that we trained. It's like we made some improvements over Mila's work, but still the humans were able to win 22.5% of the time against our pure supervised learning policy network. But when we had them play against SearchBot, where it's doing this equilibrium search on each turn, the humans were only able to win 5.7% of the time. And since that's below 14.3%, that means that they are losing to the bot. Now, this is in the setting where they're playing against 6 search bots. So it's not, it's not the most important experiment, but it's just one other thing to look at. Yeah.
Yeah, I was gonna ask about that setup, like choosing to do this as a single human versus 6 bots. I would think that it would get sort of easier for the humans as there are more other humans to work with.
Yeah. I do think that the most important experiment is this one where we played anonymous games against real humans on webdiplomacy.net. So there we scored top 2%, which I think is very good, but is not top human level.
Can you go to the slide before? Actually, this one. What's the BR bot? That looks like it scored 67% against.
Oh yes, that's a good. Yeah, so I didn't want to go into all of these, but BR bot is it's a bot that's trained to beat DipNet. So it's like trained through reinforcement learning against DipNet to try to like maximize the score against DipNet.
Yeah, how does it do against your bot?
I believe it loses. So it's BR bot. So yeah, you can take like one BR bot against 6 search bots. It only scores 11%. So it's losing to 6 search bots. And if you take, if you take one search bot and play it against 6 BR bots, the search bot will score 17%. So it will beat 6 search bots. Sorry, it'll beat 6 BR bots. Yep.
Is it the case that like many actions are somehow similar and you could cluster them and sometimes before doing the regret matching step so as to like make it easier reduce that answer?
Yeah, that's a good idea. We decided not to do that. It might have been a good design choice to do something like that. Hard to say, but this is ultimately the path that we chose. We decided to keep every single action unique. Yep.
Kind of related to this question, I didn't get the sampling of the actions from the neural network.
Yeah, so we have this like, because the game, involves moving each of these units that you control, the action space is enormous. It's like 10 to the 20, 10 to the 40, something absurd. And so what we do is we just look at, we've trained a policy net on the human data. Now that policy net, we can sample from it and get an action. Where when I say action, I'm referring to an order for each unit that we control. So we just sample from that policy net like 10,000 times, and it will sample the same thing multiple times out of that 10,000 sample. And so we just like, look, after we sample this 10,000 times, sample from this policy network 10,000 times, what are the 50 actions that we've sampled most frequently? And we put those 50 actions into this matrix and just ignore all the other ones. So we're only able to play one of those 50 actions, and we're also assuming that the other players are only able to play one of the 50 most common actions that we've sampled for them from the policy network. Okay. So takeaways. Regret matching works well despite not being in a 2-player zero-sum game. And SearchBot is able to get to the top 2% of players on webdiplomacy.net. That's strong human level performance, but still far from superhuman. There's a big gap between top 2% and superhuman. So how do we get to superhuman? Okay. So a natural follow-up, we are on each turn doing this search where we're computing on a policy given the value net that we've trained through supervised learning. And there's a really natural follow-up question, which is, can we use this approach to improve the value net? Like obviously on each turn we're computing a better policy, but can we then use the outcomes of these self-play games to improve the value net? And the answer is it's complicated. We had a paper called DORA, Double Oracle RL for Action Exploration, that basically does this. It's just like what I described the SearchBot thing, except at the end of the game, it will look at the values of all the players that from the terminal end state and add that to the training buffer for the value net. Now, in two-player zero-sum games, this is guaranteed to converge to the Nash equilibrium. And in fact, we found in two-player zero-sum versions of diplomacy, there's actually a variant of diplomacy that's two-player zero-sum and is quite popular with humans. We find that it works extremely well. We played against some of the strongest players of this variant of the game, and the bot won 86% of the time. This Dora bot. So what happens when we run it on the 7-player version of the game? Well, we get some very interesting behavior. So this is, I want to be clear, this Dora bot is trained completely from scratch. We toss out all of the human data. We just train it purely through self-play. Kind of like very, very similar to how AlphaZero works, where at the end of each game, it will use the game outcome to improve its value net. And it will do this iteratively as it plays more and more games. So what we find is if you take one Dora bot trained purely through self-play, let's start with the search bot. So you take one search bot, which is the previous bot that I mentioned that does this equilibrium search thing on each turn, but uses a human value net, and play it against 6 Dora bots. Search bot only wins 1% of the time. But if you take one Dora bot and play it against 6 search bots, Dora only wins 11% of the time. Now remember, if you are equally strong as your opponents in this setup, you're going to win 14.3% because it's a 7-player game. And so what this means is that one Dora playing against 6 search bots is losing, and one search bot playing against 6 Doras is losing. Now, how can this be? Well, this is very strong evidence of multiple equilibria in diplomacy. Basically, the 6 agents, even though they're not trained to, collude, are essentially playing very similar equilibria, and so they're like playing optimally given how the other players in the game are playing. And this poor search bot that isn't familiar with this equilibrium is doing something totally radically different that just like can't cooperate with these other players in the game. It's kind of like, if you speak French and you're stuck in this game with 6 English speakers, you're probably not going to do that well because you can't even like talk to them. Or if you're, the one person that drives on the left side of the road and we stick you, in a city with all people that drive on the right side of the road, you're probably going to be the one that gets into an accident. That's what's happening in diplomacy when we train these different agents. Yep.
So just to understand, like Dora is search bot, but you keep updating the value function based on self-play.
Dora is search bot, except we don't use any human data. Search bot is the value function comes from the human data, and also at the end of each game, Dora we update the value net. So we train the value net through self-play. Okay, so this is, I think, the key, a really key result for diplomacy, because like I said, in 6-player poker, we didn't have this problem. We trained a bot through self-play, it does great against humans. This shows in diplomacy that's not enough. And in fact, we actually ended up playing Dora against real humans, and it did really poorly. If you stick one human in a game with 6 Dora bots, the human will get totally destroyed. But one Dora bot with 6 humans does really poorly.
Did you try an experiment whether you have all different bots and one human?
Yes. With one human? We haven't tried that. We did try experiments with a bunch of different bots. That's been one of the metrics that we've been looking at to see like, okay, internally, like how do we think things are looking? It's like pretty interesting results. Dora there also does quite poorly, but it really what this is saying is that what does it mean to do well in diplomacy? You can only define that if you define the population that you're playing against. Like if your population is a bunch of Dora bots, like all Dora bots, then Dora is probably the optimal policy to play. But if your population is a bunch of humans, then Dora is not the right bot to play. And not even just humans, but you have to specify the strength level of the humans. Like if you're playing against a bunch of expert humans, the optimal policy might be very different from playing against a wide range of humans. And so diplomacy is a domain where this actually matters. Like chess and Go and poker, that is actually not an issue, right? Like if you take AlphaZero and play it against a weak player, it's going to win. If you play it against a strong player, it's going to win. And with our poker bots, if you play it against a strong player, it's going to make money. If you play it against a weak player, it's going to make more money. It might not make as much money off of them as like a really, really strong player would, but it's still going to beat that weak player. But here in diplomacy, the optimal policy for playing against the optimal policy depends on the population of other agents, and I think that's a really difficult aspect of the game. Yep.
So I wonder if there's like value in like adapting your estimate of the value function while you're playing the game, right? Like what I understand here is that Dora is like trained in like an offline setting.
In a what setting?
In like an offline setting, like you train it with self play. You
Mhm.
never actually expose it to human level play in as part of its training.
Mhm.
But while you're playing against humans, can you make maybe like adapt like your own estimates based on like what you're currently seeing is happening?
Well, you would have to adapt. Like in theory, the bot is doing that within the game. Like if you have access to the history of moves, then the bot can adapt to the history of moves that it's observed. Now, there's another way you could adapt, which is like adapting between games. Like let's say like it's playing a bunch of games and it's understanding like, oh, these players appear to be like of this population distribution. Like they seem like weak players, not strong players, or they appear like strong players, not weak players. And so you want to adapt between games to account for that. That we've done some research on doing that. It's kind of complicated, so I won't go into it right now. But
I kind of didn't get your adaptation point. Like at every step, like your value function is being estimated. It has some own estimate of its value function, right?
The value function is a function of, at least in theory, it's a function of the board state and then also the history of moves of all the players. So because the history of moves is an input into the value function, it is adapting to what it's observed in the past.
Right, but during training, the kind of moves that it sees are very different from the kind of moves that humans are doing. Right?
Yes, but that's certainly a problem with the self-play training. Yes, that's probably why self-play doesn't really work by itself in diplomacy. Yep.
Just to make sure, the Nash equilibrium is defined that if all players are in the same equilibrium, then that is the best you can do, right?
Yep.
So if there are a couple of equilibriums, you could actually do worse.
Yeah, a Nash equilibrium means if all the players are playing the same playing in a Nash equilibrium, like the same Nash equilibrium, then you want to stay in that Nash equilibrium. Yeah.
I was just making sure because you said this is evidence for multiple equilibria.
Yes, multiple incompatible equilibria. Yeah. Yes.
You said that one of the problems was that there's not enough human games recorded in order to learn from them. My question is that, of course, not all the games are have the same like informativeness in some sense. Some you have two games, two repeated exact games, then the second one doesn't give you a lot of information. Do you have like a method to determine which are like the most informative games or most informative states, so as to maybe fabricate them and train with them?
I didn't follow that. Can you repeat that?
Yes.
Yeah.
So there might be some games that are not games in like the general sense, but like plays that are more informative for your algorithm than other ones. For instance, if there's like a lot of collusion, that might be more informative than if everyone is playing independently. And my question is if you have like a measure of how informative a certain
like if you could measure the information content.
Right.
This is kind of baked into the training process already. That like it will adjust this policy more if the result deviates from what it expected. So I guess kind of yes, but we don't do anything explicit here that's not done in general machine learning. Yes.
I have another question as a human player of diplomacy. How much do you like use your prior knowledge of the players you're playing with if you know them from previous games? Like, does that influence your gameplay? If you're like, well, this guy stabbed me in the back last times, or this guy usually plays in this way, and you use some sort of priors on the players themselves?
I think that is a big factor of the game, actually. Yes. The games that we were playing on webdiplomacy.net were anonymous games, and actually gunboat diplomacy is almost always played with every player being anonymous, so nobody knows who the other players are. And I think it's very different if you know who the other players are and you have a history, and you can like I said, the optimal policy is only defined given the population of players that you're playing against. And if you know who you're playing against, then you know what the population of other players is. Yes?
I have a question. So here, like you have like a slightly different technique than from what like AlphaGo and so on is doing, right? So could you use like a similar technique to like play Go or chess, for example? Like it seems like a very general technique.
Yeah. So I think actually Dora is very similar to how AlphaZero is trained. The only difference is the search technique that's used. So AlphaZero doesn't work for games that involve simultaneous moves or imperfect information because it doesn't understand the concept of like mixed policies or private information. You could actually run this. You could run Dora on Go. It wouldn't do as well as AlphaZero because like the search algorithm is like AlphaZero uses Monte Carlo tree search, which is really, really good for deterministic perfect information games like chess and Go. Does not work well, does not work at all in poker or diplomacy. This search algorithm, because we're only looking one move ahead, it's probably not going to do as well as Monte Carlo tree search because Monte Carlo tree search is like looking much farther ahead. But it would still probably play a decent game of Go. Okay, so takeaways. Dora, trained from scratch, is superhuman in 1v1 diplomacy, but Dora doesn't do well when playing with 6 human-like bots, or 6 humans, as we found out later. This strongly suggests that self-play from scratch is insufficient for diplomacy, which is very different from all previous game AIs. And I would argue is very similar to the real world, where self-play is probably insufficient. So we need to understand the human equilibrium, and yeah, that's the important thing. We need to understand how humans play.
Sorry, one more question. About chess bots, I know like people have been trying to make chess like chess bots that play more human-like. So even if you play like low-level chess bots like online, you find that they make like really weird moves that, or really bad blunders that like humans would not make. So I know like there have been like some attempts, I think called like Maya or something, that they try to make like the bots policy match like human policy. So like could something that like help with the problem that you have here?
Yes, very good point. And I actually cover Maya in like 2 slides.
Okay.
Yeah. So yes, that's where we're going. Okay, so this leads to our latest work, which is on building strong and human-like agents with KL regularized search. And this is a collaboration with several authors, in particular my intern, Phil Jacob from last summer, David Wu, my collaborator, and Gabriela Farina, my former lab mate from CMU, who all contributed a lot to this paper. Okay, so I want to take a step back and talk about search, because I mentioned our diplomacy bot used search, even though DeepMind didn't use it, Mila didn't use it, and the reason why we chose to use search is because we found in pretty much all previous games, search and planning has been extremely important for achieving strong performance. And in fact, I think this is one of the most interesting slides that you'll see in this whole talk. So this is a plot showing different versions of GoBots. So we have like AlphaGo 0, AlphaGo Lee, which is the one that played against Lee Sedol. And then like the red lines are previous GoBots from before 2016. And the y-axis is ELO rating. So that is a measure of strength. And top human performance is around 3,600 ELO. So for example, you can see AlphaGo Lee, the bot that beats Lee Sedol, is right over that line of superhuman performance. And the latest and greatest version of AlphaGo 0, is around over 5,000 ELO. So very, very superhuman. But what's really interesting is that if you take out the Monte Carlo tree search that's done at test time, and just look at the raw policy net of AlphaGo 0, the ELO rating is only around 3,000. It's actually below superhuman performance. And what this shows is that search, and by search I mean like this planning ahead of what you're going to do, understanding like the consequences of your next action, is critical for achieving superhuman performance. And in fact, this is only if you take out the Monte Carlo tree search at test time. This is still with Monte Carlo tree search used at training time. And in fact, even today, nobody has trained a superhuman Go AI like nobody has trained a neural net that is superhuman at Go. I think a lot of people find this surprising because AlphaGo is like hailed as a major accomplishment of deep learning, and in fact, deep learning was a big component of the AI, but it wasn't the only component. And so far, nobody has trained a raw neural network that has been able to beat a top human in Go. So that shows, you can see how big the gap is here by adding Monte Carlo tree search. And in fact, this isn't unique to Go. If you look at pretty much all the previous game AIs, they've all involved some kind of search or planning. Chess used alpha beta pruning. You know, in poker, the big breakthrough was figuring out how to do search in poker, and that led to a dramatic improvement. This is when I really appreciated the value. This is when I really appreciated the value of search, when I saw how big an improvement that we got in our poker bots by adding search. Hanabi, diplomacy too, we're seeing huge gains from being able to use search. And so I really think that this is an underappreciated component of AIs today. And yeah, the big challenge, of course, is that all these search techniques are kind of customized for the domain. Like AlphaGo used Monte Carlo tree search, which doesn't do well in poker. The search techniques that we use in poker and diplomacy don't do well in Go. And so I think one of the big open questions in AI today is how do you get planning and search to be as general as neural nets are for things like reinforcement learning? Yeah, big underappreciated question in mind. Okay, so that's the motivation for why we care about using search in the first place. And I'm also going to argue that humans do something very similar to search when they're playing. Like when you're playing chess and Go, you don't act instantaneously. You spend like 15 or 20 seconds to plan out what your next move is going to be. And what I'm going to show is that we actually get better prediction accuracy of human experts in chess and Go if we add search, if we do it the right way. Okay, so taking a step back, training on expert human data. Okay, so Maya is a chess bot that was trained to play like a human. It was trained on hundreds of millions of human chess games. They have different models for different ELO ratings, and it achieves state-of-the-art accuracy in predicting human moves, including experts. Interestingly enough, this Reed McIlroy-Young, the main author of this paper, is now interning with us at FAIR. So for high ELO, it achieves state-of-the-art accuracy in predicting human moves, including expert chess players. But one interesting aspect is that for high ELO models, Maya is around 100, 300 ELO points below the target ELO rating. So you train it on like 2100 ELO humans, it only ends up being around 1800 ELO. So what's going on? Well, my hypothesis is that approximating human planning is actually really difficult for neural nets. There's a lot of subtlety to the strategy in chess, and the neural net is simply like having a lot of trouble capturing the planning that expert humans are doing in chess. And the evidence that we have in favor of that is that there is one version of chess where there is no Maya ELO gap, and that is bullet chess. Bullet chess is a version of chess where the timer controls are so low that you don't have time to plan ahead. You just have to basically act out of instinct. And there's no Maya ELO gap. So my hypothesis is that what's going on here is that search and planning are more important for modeling human behavior in situations where humans spend more time planning. And so this is why neural nets today are really, really good at tasks that are almost instantaneous. So they're really good at image recognition, really good at real-time strategy games. So Dota 2 and AlphaStar, those bots didn't actually do any search or planning, but they still did really well, and that's because they're more intuition and reflex focused games. Natural language processing is also a lot of it is just kind of like intuition and just kind of stream of consciousness. And in fact, one of the big complaints about large language models today is that they kind of sound like a stream of consciousness. They're not really planning out what they're saying. But when you go more to this extreme, like games like chess and Go and diplomacy and poker, humans do more planning. This planning component is more important, and that's where you see raw neural nets really struggling, actually. Okay, so this is all to say, search and planning are, I think, really important for making a compelling, making a strong diplomacy bot. But we have a problem here. We can do pure supervised learning on human data, and that gives us fairly high human prediction accuracy, but mediocre performance. On the other hand, we can do self-play reinforcement learning and search like AlphaZero and Dora, and that gives us very, very strong performance, but very inhuman policies. And again, if we want to do well in 7-player diplomacy with real humans, we have to be able to model how humans play. And self-play reinforcement learning and search is not doing that well. So our solution is to add a KL regularization to the search. We regularize the search with a penalty based on the KL divergence from the human supervised learning policy, what we're going to call the anchor policy. And we have a parameter lambda that controls the magnitude of this penalty. Now, interestingly, this is already kind of baked into Monte Carlo tree search. It's also widely been used in RL previously. So for example, AlphaStar did this, though they did it more to like aid exploration rather than to explicitly model human behavior. Now this is also, I think, a really fascinating plot, and it's actually for chess and Go. It's not for diplomacy. So on the y-axis here, we have win rate versus a raw neural net model. And on the x-axis, we have top one prediction accuracy. So how well are we able to predict the human expert move in chess and Go? So yeah, this is where like this raw model right here is trained on a bunch of human expert chess or Go games, like hundreds of millions or something. And you can see the human prediction accuracy is around 53%. The win rate versus the raw model, well, it's 50% because right now we're playing against itself. The green dots are if you add Monte Carlo tree search with varying levels of regularization. So if you add a huge amount of regularization, like this dot over here, if you add very, very little regularization, your win rate is going to be very high, but your prediction accuracy is going to drop off a lot. So you're going to be really bad at predicting human moves. But for appropriate levels of regularization, something like intermediate values, you have very high win rate, and also your prediction accuracy of the human chess moves and Go moves goes up. And this is like, again, this is a pretty radical concept. The central premise of machine learning is that if you want to predict, a test set, you collect a bunch of data, you train on it, feed it into a neural net, and then, output the neural net is your prediction of the test set. That's the way to get highest prediction accuracy. Just train a giant neural net. But this is saying like, no, actually, if you want to improve the prediction accuracy in chess and Go, you can do better by adding Monte Carlo tree search on top of that with an appropriate regularization. And in fact, these two plots are very similar. They look very similar, even though there are two very different games. So I think there's something quite interesting going on here. So yeah, this allows us to do better and achieve higher prediction accuracy in chess and Go. And we wanted to try something similar in diplomacy. So we modified our regret minimization algorithm to also incorporate this KL divergence penalty. I won't go into the details of the algorithm, but basically we modify the regret minimization algorithm to incorporate this KL regularization. And we get this plot. So there's a lot going on here. I'll just kind of cover the highlights because we're running very short on time. Y-axis is average score. X-axis is prediction accuracy. We have Dora, which is the orange dot over here. So it's very low on prediction accuracy, also very low on score when playing against human-like bots. And all the way on the right, we have the bot trained purely, the blue dot is trained purely through supervised learning. Very high prediction accuracy, very low score. The green dots and purple dots are various levels of regularization that you add on top of the search bot. And so you can see if you add a little bit of regularization, if you add a lot of regularization towards the imitation learning policy, you get a prediction accuracy that's roughly the same, in fact, a little bit higher than pure imitation learning, but the score goes up. And so we can create better bots that are also human-like in this way. Okay, so we use this to create human-like bots that are actually quite strong, and then we add this to a pool of agents and we train against them. And then this led to us producing a bot that's basically compatible with how humans play and also plays well. And we ran a tournament on webdiplomacy.net where we played this bot against actual humans, 50 human participants, and the bot came in first place. So I think it's fair to say that this bot is now performing at an expert human level, if not superhuman level, in no-press diplomacy, gunboat diplomacy. Okay, takeaways. Kill regularized search and supervised learning beats supervised learning alone at human prediction accuracy in chess and go. In no-press diplomacy, that is gunboat diplomacy, this allows us to better model human players than any prior approach and allows us to produce an expert level bot in this game. And this suggests that kill regularized search may be generally useful, not just in diplomacy or chess and go, but also more broadly in modeling human behavior. We have similar results now also in the game of Hanabi, and I think that this actually can be used for real-world situations like self-driving cars. In fact, I'm really excited because this is the first time that I've ever worked on something where I'm like, I actually see clear applications to the real world with this technology. Okay, so looking ahead, I think it's safe to say now that we are done with no-press diplomacy, that is the no communication version of diplomacy. We have an expert level bot in this game, but this is just the beginning. This is where things now get interesting. What happens now will be add communication to these bots, where they can privately coordinate with other agents when negotiations are unstructured, when there's free-form communication that, we ideally would be grounded to the states and actions happening in the game. So I'm really excited about where this is going to go in the future. I want to plug diplomacy as a benchmark for AI research. I think this is an excellent domain for multi-agent learning. This is a real game played by real humans, spanning the spectrum from beginners to experts. It's easy to score. It's not a cherry-picked domain. This has been around for years, for decades as a benchmark, and it's been around as a game for 70 years now. There's lots of data from motivated humans, not just triggers. And this data is publicly available. And also, the complexity of the game comes from the multi-agent interaction. It does not come from the environments. This is a turn-based game. The state space is fairly simple. The iClear search bot paper that I mentioned required no training, no reinforcement learning, and runs on a single GPU. So this is very much accessible to academics. And there's a growing community consensus around this game. So I've mentioned some publications from our work at FAIR. DeepMind has also done work on this and is continuing to do work on this. Mila, MIT, Oxford, University of Maryland. So it's always great when more researchers are working on the same domain. And all of our code and models are published and open sourced. So you're welcome to build on them, and we're happy to help you if you have any questions about it as well. Okay, so I will stop there, and thank you for your time.
Is there any other questions? Any questions on Zoom? I haven't seen it. Okay, I think people got their questions out.
One question. So you, to get this performance, you have access to data generated by humans, but I can imagine that maybe not in all cases you have access to such a large data set. Do you have any ideas on how to get more human-like behavior without having explicitly that supervised learning data?
You mean like without any human data or without?
Yeah, are there ways, or do you? It's a bit of a philosophical question, but like to get more human-like behavior without having access to actual human data.
Right. This is very much a debate in the multi-agent RL community today. So there are several researchers that take this perspective that we want to try to get human-like behavior without using any human data. My philosophy when it comes to research is very different. I am skeptical of that research direction because I think it's really hard. I think the answer is yes, you could, but only by encoding a bunch of heuristics. And so it's, if it's a choice between encoding a bunch of heuristics or learning from actual data, I think the history of machine learning has said the better approach is to learn from actual data. So I think there is a lot of research in this direction of trying to get more human-like behavior without relying on human data. But historically it hasn't done that well, and I think even if it did, it would be overfit to the domains that they're looking at because there's so much of a focus on like trying to come up with clever heuristics that work for this domain, but probably won't work for other domains.
Can everyone on Zoom hear me? I have a quick announcement for the summer school. We've had some more recent changes in schedule. Apologize for all of that, but please check the schedule. In the mornings, our speakers keep coming to us with like requests to move around. So sorry about that, but we have updated the sheet. So it's the same for this afternoon, but like there were some changes tomorrow. And so make sure everyone on Zoom also make sure you're checking the schedule every day. We are unfortunately having to move things around more than we would like. So, all right. The other thing I would like to say before we go is that a few of us are going to have lunch with Noam, and we have room for 2 spots. If any 2 students would like to join us, we're going to have lunch a couple doors down before the afternoon session. So come talk to us up here and we'll figure it out. And otherwise you can go to lunch wherever you are planning. Thanks. Thanks, Noam, again.
Okay, so I think like many algorithms are used by industry are not suitable for science. And so I'll give an example of this. We had a iClear paper with collaborators at DeepMind earlier this year on learned simulation for turbulence, like fluid prediction. So the first row is the ground truth simulation. Second row is the learned simulator. And it's about 1,000 times faster because it's operating at a lower resolution. So this is really useful, but I think as scientists, what we really want is like insights. We want to understand why the model could do this. Like what is the new scientific insight to kind of point us to like new theory, basically. So for example, like I don't know if anybody knows Kepler's law. So this is the it's a formula which relates the period of a planet to how far away it is from the sun. This was discovered by Kepler, and then about 100 years later, Newton discovered gravity, not from an apple, but from Kepler's law. So it was kind of, it motivated theory development. So another example is like Planck's equation to describe the black body spectrum of light. That was actually an empirical function fit. Like it was just, he fit some equation to data, which worked, but we needed quantum mechanics to explain that. So I think a lot of times in the history of science, we've observed some pattern in data and then developed a theory to explain it. I think this is a very successful mechanism for science. So I showed these plots on my first tutorial, and if you remember, you can get this kind of neural network here to predict this spiral, right? But the major problem, I think, with this, from a science perspective, is like what's the relationship between these? Like how does this neural network actually compute that? For 2D, okay, maybe you could reason about like, it's like planes and it's like superimposing them. But I think it's really missing the insights that we need in science to kind of propel us to new theories. So I think it's interesting to think about like, okay, if machine learning wasn't around in 1609, would Kepler have discovered Kepler's laws? Or would it have just been like a black box neural network and you fit it to data and it works and you're happy? Or like, would that have led to gravity then? So there's this concept in software development called technical debt. So if I'm writing some code and I choose like a really easy solution and I do it really quickly, that might save me time in the short term, but in the long term, when I need to go back into my code and kind of rework it, it's more expensive. So there's kind of like a similar idea for science. Like and deep learning. So deep learning, even though we can solve complex problems quickly, there's this concept of technical debt. So whenever you need to, say, retrain a deep learning pipeline, it's expensive, and it's not it's kind of it's similar to kind of choosing a better solution earlier. So I really think when we use machine learning in science without really kind of understanding what the machine learning has actually done, we kind of get this scientific debt where we don't understand what's going on, and then we try to attack like another problem, but we also don't know what's going on in the simpler problem, and it just kind of stacks up. And we, without really understanding why this prediction is working, say. So you can see this in the real world. So there was this like big paper in 2018. They had trained neural networks to detect pneumonia in patients. And it was later discovered this model was, here, let me hide it. This model was basically looking at, there's like a little piece of text here, and the model was just like reading the text in the background of the image. Oh yeah, you can move it.
We don't need to see the picture, right?
Yeah, you can minimize it. So the model was basically like just looking at the diagnosis, and it was just like reading the diagnosis and not even looking at the lungs. And I think this problem kind of manifests in deep learning. If we don't understand what it's doing, it could just be looking at artifacts of our data and not really learning something like physically meaningful. But yeah, I mean, I'm like, to be clear, I'm not a deep learning skeptic. I use deep learning. I do deep learning research. I just think it's important to be aware of this. So what I am interested in is, can we use machine learning to get new scientific insights rather than just predictions? So I want to go from ML model to insight. So here's one strategy for doing this. There's other techniques, but this is, I think this is a way you could do this. So the first thing, which Wenda talked a bit about, is you want to make your ML look like your existing algorithms. So if you have some scientific pipeline and you understand most of it, but maybe there's like one function in your algorithm which you don't really understand, maybe you just learn that function and you leave the rest there, and you just kind of do gradient descent through the rest of the pipeline. I think that both helps you get a better model, and it actually makes it easier to get insight. So for example, so when I talked about Hamiltonian, I like Lagrangian neural networks. That's why I was like, why not Lagrangian? But Lagrangian neural network is basically a regular neural network. If you take the position and velocity of some system and you predict the acceleration of the system, if you do this with a normal neural network, you basically get a loss of energy over time. Like you get this artificial diffusion in your model that wasn't in your training set. And so the way to get around this is basically impose energy conservation in your system. So if you know a little bit of physics, there's this concept called Lagrangian mechanics. The principle is, rather than predict the acceleration, we're going to predict this number called the Lagrangian. The Lagrangian is a function of position and velocity, and you can relate it to the acceleration through the Euler-Lagrange equation. So the time derivative of partial L partial velocity is equal to partial L partial position. So what you can do is you can rearrange this differential equation and you get this formula. So you kind of expand the time derivative and you can identify the acceleration here. And then when you solve this, you get this equation, which is acceleration in terms of just position and velocity with this learned Lagrangian. So you can basically do this with a neural net. You predict the Lagrangian, you run it through your equation, which is like your existing physical framework, and you get energy conservation, like for free. Like you can still learn arbitrary dynamics, but you get energy conservation just because you put in your existing physical understanding. So this is like a regular neural net, and this is a neural net that you've given like Lagrangian mechanics. So the regular one, you get like this artificial diffusion that wasn't in your training set. The regular one, or the Lagrangian, conserves energy. Yeah.
So the regular baseline is like neural.
Yeah. Yep. Yeah, exactly. Yeah, it's predicting the acceleration. Yeah. Yeah.
For the second derivative, do you need to compute gradients to the
Sorry?
You need to compute the gradients.
Yeah, you have to compute the gradients through this formula, which can get pretty nasty for like higher order system or like higher dimensional systems. So there's some tricks, because this is a matrix inverse, which can be like a bit expensive. So there's some tricks like you can do like a forward and backward derivative, and it's like a bit more efficient to get the matrix derivative. But yeah, it is pretty expensive. Yeah. Yeah. So the difference between this and Hamiltonian, you have to know the kinetic energy of your system beforehand, because you have to be in the momentum coordinates, whereas this is just the velocity coordinate. Yeah. So I think, let me think. Actually, I think I'm going to skip this part, but basically, yeah. So this is like, so the Lagrangian is kind of like a toy example. There's this thing called a graph neural network, which is another way of kind of imposing existing physical structure to neural networks. And I think this was a really nice example of like what you can do with that. Like what's the coolest thing you can do. So this is a fluid prediction. The left side is the ground truth, the right side is prediction. It's a neural network that has like different rotational equivariances in it. And let's see. Yeah, so the predictions, like they look really physically accurate. And basically this model is evolving forward like all the particles. So every single particle, the neural network is predicting the next step. And so like if you look at the data representation, oops, it is like, this is the data representation. Like it's particles, so it's a smooth particle hydrodynamics code. And the graph neural network is basically like time stepping every single particle. And you get better predictions because you're using an existing physical framework. And yeah, so this is by some collaborators at DeepMind, and we did this other work with them, which was basically, because you're using an existing physical framework, you can kind of like poke around inside the neural network and show it's actually like learning physics. So this is a 2D system. And basically like if you look inside the neural network and you kind of like, you turn up the regularization, you kind of like, you punish the network for redundancies. Basically it finds two-dimensional like internal state space. And that basically means it is finding like Newton's law of gravity for this system. So not only like imposing physical frameworks on your learning gets better results, but it also makes it more interpretable. Like you can show that my network is actually learning physics. Yeah.
So is it like that it converges to two-dimensional external representations because you need definitely two?
Yeah, two is the minimum number of dimensions. Yeah.
Okay.
So like if it was one less, you couldn't really do anything. But it doesn't need more dimensions. Yeah. And so like you can go further than this. So you can actually look at like what these dimensions are, and they're actually equal to the force law rotated. So it's like it is actually learning Newton's law, which is cool. So I think like these types of this paradigm of like using existing physics in your neural network, it gets you better performance and it improves interpretability. So, okay, so yeah, we want to make ML look like scientific frameworks. The second part, which is a lot of what I work on, is like, okay, given one of these networks, like how do we get insights out of it? How do we learn something new? So there's this other machine learning technique called symbolic regression. Basically, given a data set, say we have like X examples of X, we have examples of Y, we have examples of output, we have a symbol set. We have like a plus symbol, cosine, X and Y. We can use a genetic algorithm to kind of like rearrange these symbols until this tree like matches our data set. So rather than like fitting parameters in some very flexible model, we're going to rearrange symbols. So yeah, I'll give a short demo on this tool. So I have this tool Pyser for doing this in Python. Basically, the way it works is any equation, you represent it by a tree. This is like your genetic code. So this tree represents this equation, which represents like a curve in data space. So it's a model. The genetic part, like a lot of genetic algorithms are literally inspired by like evolution. Like you look, okay, what happens in evolution? Let's do the same thing for this genetic representation. So here our genetic representation is a tree, and we're going to do mutations. So like randomly mutate plus into minus, and it like changes our expression. Another thing we could do is like breeding equations. So if you have two trees like this, you can breed them. So maybe they're both actually okay equations. So they like win the tournament and they breed, and they swap parts of their genetic code, which is what happens in evolution, and you get new equations. And so this one is actually like the correct one. But this simple algorithm of like randomly mutating and combining equations, it lets you explore this symbolic space actually like kind of efficiently. I mean, it is still like it doesn't use gradient information, and there's some ways to use gradient information, but it's like a very bumpy optimization surface. Yeah, I'll give a demo after actually, so we can skip this one. So another thing you could do, which I really like to do, is once you've trained like a neural network model, you can use symbolic regression to kind of distill it into an equation. So if I have this neural network model I've trained on some problem, and since I am a scientist, I want to look at an equation because I can understand an equation, I can relate it to my existing theories. So what I can do is I can say, okay, I'm going to record the value of this neuron, record the value of this neuron, and say this neuron, until I have a lot of examples of those. And then I'm going to fit an equation to that. So you can do this for like the GraphNet example I showed, and you can actually get Newton's law. Yeah.
Very general question.
Yeah.
Like depending on the resolution of the output of the network, you can fit many very different functions to the same output. Some of which will not be as useful to you, or you can confuse you. So how do you know? Do you have any way to actually parse out what could be?
Oh yeah. Okay. So there's some different like things to this. So like for one, if you impose a sparsity constraint here, like you ask for as few neurons as possible, you can actually like you can prove that it will get like the true force law subject to a linear transformation. So it's like you will find like a random rotation of the force law, but you can still you still get the same expression at the end of the day.
Yeah, but this isn't like specifically in the function where you know the output, right?
Yeah.
You know that there's the fourth law. If I want to do it for something where I don't know the output, this is more problematic.
So yeah, I mean, we've done this for like systems we don't know the force law, and it still seems to work, like this sparsity constraint. It's just like it reduces it to the fewest degrees of freedom to find the correct model. Like there are still some degeneracies, especially like so normally what happens is you have an operation in this space that eliminates the degeneracy. So like maybe you have a summation over a sequence, and that eliminates the degeneracy.
So you somehow impose an operation that you know will help you like eliminate the degeneracy.
Yeah, generally, like I think if you had a degeneracy, it would be like unsolvable. So you want to impose like, I'll give an example. I actually have like a time series example we can look at later. So I think like,
One question. So did you combine this like with your Lagrangian neural networks, for instance, to get the Lagrangian and stuff like that?
So that actually works. So the Lagrangian case is interesting because Lagrangian mechanics is it has a gauge invariance in that you can multiply L by any constant, you can add any constant, and it'll be the same dynamics. So the equation you get at the end is actually like the true L multiplied by something plus something, but you do actually get like the correct thing.
That's very cool.
Yeah, and you can pose like additional constraints like L2, like you ask the network to be like small output, and then that eliminates like the plus constant degeneracy. So I'll talk about examples now. So this one example led by Pablo, who's actually starting a postdoc here this fall. We wanted to see, can we find Newton's law of gravity by just observing the solar system? So like, we don't even know the masses, we don't know the dynamical model, we only get the positions of planets. Can we find Newton's law of gravity? So the model for this is we have positions of every planet in a 3D space. We have accelerations of every planet in a 3D space. We say every planet has an unknown parameter. We call it VI. So we just assign a random number to every planet. Okay, and we're gonna learn what this is. We also write down this is basically like a neural network model for some force function. We don't know what this is. The model we want to solve is for a planet I, we sum over all other planets, J, we sum this function F, which takes their displacement from each other, the parameter, which will be mass, but the model doesn't know it, of planet I and of planet J. So the next thing we do, you have to enforce Newton's law of motion here because there's a degeneracy. Basically, like, if you don't assume F equals ma, the model could learn like F equals m squared a, or like m cubed a, and get like the same dynamical model. So that is the degeneracy here. So you assume that my force law is divided by the unknown parameter. So we're going to learn this, and basically we learn the unknown mass parameters and the function at the same time. So we gradient descent through everything. And so the data is basically like, we have data from NASA's Horizons project. It's basically like 31 bodies. So like all the planets and a bunch of moons, and we just try to predict the dynamics. So this is the original model. This is the sun, and then 4 planets with their predictions in wireframes around them. And so this is like their data representation. So they have like edges between them. And let's see. So the first attempt at this didn't really work. I mean, it does okay, but like some of the predictions like obviously diverge after a while. So we tried to look, okay, why is this? Like it seems okay, but like something's obviously wrong. So we tried that approach I mentioned earlier. We have this neural network. We record the inputs and the outputs of the neural net. And we try to find, okay, what is the expression that approximates that model? And we get this. So in symbolic regression, basically what you normally do, you record the best expression at each complexity. So this is my best expression for complexity 3. So x divided by r. There's 3 symbols. And that one's like bad, obviously. The next expression is x over r plus a constant, which is complexity 5. Then complexity 7, x over r times r plus a constant. We go down, yeah.
Complexity is just the number of nodes in the tree.
Exactly. Yep. Yeah. Complexity in general is like just like a philosophical black hole. It's just like a mess. And like, so we just chose the simplest thing. Just count them.
Could also could have a very stupid tree.
Yeah. Yeah, but it would be like eliminated because we only save a tree if it's better than every tree simpler than it. Yeah. So the y-axis here is basically like the accuracy complexity trade-off. If you get like a really good bang for your buck, you're gonna have a big score. So this curve over there is Newton's law of gravity. So you see this is constant mass 0, mass 1 times x over r cubed. So this is force along the x direction. And that has the best trade-off. There was another one which was actually more accurate, which is this, which is like added a constant, but the trade-off was like really bad. Like it just adds like 10 to the negative 13 improvement. So it dies. So yeah, so we get Newton's law of gravity. We then put that model back in. So we replace the neural network with that symbolic model. So you would expect it to do perfectly well, but it's not that good. So you can see like the wireframe there is like, again, it's divergent. I mean, it's better than before, but it's still like, I don't know, it's still not perfect, right? So we looked at this and we looked at the learned parameters for every planet. And it turns out that many of those learned parameters, the truth is shown in blue. Many of the true parameters shown in red are like completely wrong. Like our gradient descent scheme was finding the wrong mass parameters for this. So you can see like some of the planets are actually okay, but like most of it was just completely off. So, and these are the planets and these are moons. So we thought about this, and the reason is because like going back to the very start of my talk, you remember the pneumonia example. Neural networks are very good at cheating. So our neural network was basically like inventing its own mass conversion scheme. Like given a mass, it'll convert it to like the true mass internally. and it was like cheating at our problem. So the reason for this is because we only had 31 examples. If you train a neural net with 31 examples, like it's gonna find some crazy function we didn't expect. Like we tried this in another simulation with like many different examples of mass, and it worked. But like 31 examples, it's just not enough constraining power. So, okay, then what we do, we take the symbolic formula and we just re-optimize the mass parameters. So like the symbolic formula we found, it's not like a perfect model for the neural net because the neural net's cheating. So we just like re-optimize the masses. And now it works. I mean, like now it's like literally just like, if we do get the right mass parameters, like it's literally just a model for gravity. So it should work fine, and it does. So you see like the predictions are perfect. So we can then look at the mass parameters, and they're almost all perfect. Like they're completely on the dot in most cases. Some of the moons were like pretty bad. Like this is Hyperion and Phoebe, which are two very small moons, and their estimates were pretty bad. And we looked at this, and this is just because they don't influence other bodies, so you really can't constrain them that well at all. Like it's just, it makes sense. Like those bodies don't affect other bodies, so you can't do an inference. But we do get like most planets pretty well. Yeah, so I think it's like really cool that without knowing the math or the dynamical law, you can use machine learning to constrain this system if you make a few assumptions. And I think like one of the things we want to do next is like turbulence. Like, so we have this very good deep learning turbulence model, but we don't know how it works. So maybe we can use like the symbolic regression and kind of like interrogate internal parts of it and figure out what it's doing. That's it. Yeah, so in conclusion, I think like in science, we should use deep learning, not just for predictions, but to get insights. And I think symbolic regression is a really good way to do this because our existing theory uses symbols and it uses these operators. So when we find like another new expression, we can see connections, but you can't see connections with like neural network weights. Like it looks like noise basically. So I think this is a good reason to use symbolic regression. And now I think we'll do a demo we'll do like a little tutorial of symbolic regression. So I want everybody to go to this website. So it's, it's this. If you just like search my name Picer, you should find it. And we can do a little tutorial. And I think we could, if we have time, we can do like a PyTorch thing at the end as well. Were there any questions actually? Yeah.
Is there any example of a law that was first observed like as via symbolic regression and then tested and turned out to be a good approximation of the?
Yeah, let me find it. So in the original paper, we gave like one example. I mean, it's not Newton's law of gravity. Like it's not like significant, but it's still like new. Let me find it. I think, here. So I think this law here is like a new equation that nobody knew about. It's basically like a relationship between dark matter distributions and dark matter overdensity at the core of some like dark matter blob. I don't know if it means anything, but it's like new. Yeah. I mean, it took like 80 years for Kepler to evolve into Newton mechanics, so we have time. Yeah.
Well, I do know about an example where this letter was used to actually prove theorem and not theory. So
Was this the DeepMind example?
I don't know. It wasn't.
Oh.
It might have been.
Oh, is this like the automated
Yeah.
theorem proving? Okay.
So they didn't use symbolic regression as far as I remember, but people do try to do stuff like that and try to.
Really? That's awesome.
Yeah.
Okay. Yeah.
I just had a early question. So you used the GNN for like before you did the symbolic regression, you had this method which gave you these force functions F.
Yeah.
I'm just wondering. So I guess those were like GNN messages on the fully connected graph. And so how did you parameterize them? Is it like a sum of basis functions or?
Oh, how did we parameterize the message function? So the message function is a multi-layer perceptron.
Okay.
Which takes the node values concatenated.
Okay.
So we actually gave it the displacement to kind of give it like translation equivariance. But you could potentially just give it like the absolute positions of each body.
Yeah. So how did you input the spatial information? Like, did you just really input the position vectors, or did you use did you evaluate the positions on some set of basis functions, or?
Yeah, we just input the
really
vectors.
Okay,
Yep, to the neural net. Yeah. Yeah. Yeah.
Yeah, how fast is it to find like a symbolic expression for what the neural network is happening?
Oh, it really depends. Like I could give, so I'll show you like a really quick example before we can do the demo after. So like if I do the example code, so this equation is 2.5 times cos of x3 plus x0 squared minus 0.5. That's the equation. And so I can start my model and then I can like fit it. So it's just in time compiled. So the first run is going to be a bit slow, but like the second runs are going to be faster. You can see for this equation, it's like pretty simple, so it should find it fast. We've done some searches that are like we run it for like 10 to 20,000 CPU hours to find like much more complex expressions.
Okay.
Yeah.
Is there ever a scenario where it could be faster than like actually forecasting through a network, especially if it's like really deep?
Oh yeah. Oh yeah. Oh, you mean the output expression?
Yeah.
Yeah, totally. I think like most expressions you find are going to be faster than a neural net. So it's actually like efficient. Oh yeah, so I found it. Okay. So like if I run it again, then it won't have to compile. And you can see like it's pretty fast. So it found it here, right? And then I can like see it with like SymPy, and it's the true expression. So like if you evaluate that expression instead of your neural net, it's going to be way faster.
Could you use that like to train faster in some cases where you have like a very network?
Yeah, that's a good idea. I didn't think of that, but maybe you should write a paper on that. Yeah, that's a good idea. Yeah.
So I was just wondering, I don't know how long the time scales were of your trajectory data, but do you think you could also kind of train this to discover the perihelion precession of Mercury?
Oh, that's a good question. So I think the answer is no, because like it barely struggled to find the right masses. So like I don't think it would find GR, for example. Like I don't even think it would find like an approximation of GR, because there's just not enough data. I think if you had more mass examples, maybe.
Okay.
Yeah.
Okay.
Like I think so so for those who don't know, GR was created by Einstein and then tested with the precession of Mercury. But I don't think you could find GR just from that phenomena. Like I think it's a test, but it's not a training set. Yeah. But yeah, that's a good question. Okay, so we could do a tutorial. So if you go up to this part of the GitHub, where it says Colab Notebook. And if you click on that, it's going to open this notebook. So this is a Colab notebook. You probably want to do like file, save a copy, and drive, so you can modify it. There is a deep learning component at the end. So if you go up to edit notebook settings, you can turn on your hardware accelerator. You can turn on the GPU. So I confirmed, like, we can buy you pro accounts. Like, everybody can have pro accounts. I mean, it's like $10 a month. Like, I feel like, why would they buy you like apartments in New York and they can't afford like $10 a month? Like, so yeah. But I don't know how it's gonna work yet. Like, if someone's gonna use their card or you get reimbursed. Like, it's probably too much paperwork if everybody gets reimbursed. So I don't know. Anyways. Yeah, so just run this cell. It's going to install Julia, which is the back end of this package. And then you're going to want to run the second cell, which is going to install Pycer. And then just run the next two cells as well. So that'll just like set up the installation. And yeah, that could take like maybe a few minutes. So I think in the meantime, let's talk about the actual Pycer regressor algorithm. So this is it's called a scikit-learn model. It's this Python package called scikit-learn. It is a library of like different learned models. And they all look like this. So you declare a model using some parameters. So these are my parameters of my model. And then you do model.fit. So this is true for like any scikit-learn model. So if you Google like scikit-learn, you can find like many different models which have the same format, and just try many different models on your problem. So X here is like my input data, and Y is my output data. So in this case, my input data is 100 examples and 5 features, which are random numbers. And I'm going to run it through the same expression I mentioned earlier. So it's like one example output. Yeah. Yeah.
Would have to constrain the solution.
Yeah, so I'll give an example later.
Sorry if I'm interrupting you.
Oh, no, yeah. No, it's a great question. So I have an example in the notebook of noise, yeah. Yeah, so I don't know if did it install for everybody, or no, it's still running. Yeah, it's got to install like all the Julia stuff. So, okay, so the few hyperparameters you need to worry about are binary operators. So these are like what operators I want to use. Binary means 2 inputs. So like plus takes 2 inputs, it adds them. Minus, so you can actually write these like plus, multiplication, division, and minus. So those are the binary operators. The unary operators take 1 input. Actually, let me zoom in a bit. Can people see it okay? Maybe I'll zoom in a bit more. Okay. So this parameter here, n iterations, that's just how long it runs, basically. So I actually like to just set this to like a massive number and then just quit when I'm happy, because it doesn't really converge, like it just keeps running. And then the other parameters, so prox is like how many threads you want to use, and populations is like how many different populations of equations. So each population is going to have like 30 equations running. And so like a single population is like an island of equations that live together and make baby equations. So there's 30 different islands, and they kind of migrate between each other. Yeah, it really like it tries to model evolution, like a lot of these different algorithms. Okay, so it's almost done installing. The model selection is like, once it's fit all the equations, how do you choose the equation to use? So this could be like best or accuracy. Accuracy is just like the best equation, like in terms of loss, and best uses the trade-off of accuracy complexity. In practice, I like to look through the equations and just see like, okay, that one looks like it actually is doing something physical, so I'm going to use that one. But this is like an automated way to select it. Okay, so I think it's ready. I don't know if it's ready for others, but we could start running it. So you're going to run this cell to import everything. Run this to generate the data set. Create the default parameters. And then we're going to create the model and fit it. And it should look something like this. This is just like looking for updated packages. The first run is going to take a bit longer because it has to just in time compile everything. But the second and third run are going to be much faster. Okay, so it should start soon. So yeah, I kind of prefer the IPython notebook, or sorry, the IPython version, because it the outputs are like a progress bar, which is nice, but it does work in Jupyter too. It just like prints less often, basically.
Do the same TQVM.
What?
It's TQVM, right?
So it's actually like the printout is from Julia, and it uses like this. It's because like Python hooks into Julia, and so the printing in Jupyter is like kind of tricky. But if you know a way, I'm happy to accept a PR to my GitHub if you know how. I haven't figured it out yet. Yeah, so this hopefully should start. Is it still installing for anybody? Or it's running now? Okay, cool.
You said that your population, or that the number of populations are islands.
Yeah.
Right? How many individuals are there per island?
So by default, there's 33.
Okay.
The reason it's 33 because I ran like this massive hyperparameter search, and 33 is the best.
Okay,
but it could be, you could like,
specific, right?
well, I tuned it on like a suite of problems,
Okay.
but it is still specific to that suite.
Okay.
Like I think in practice, you probably want to tune to any problem. Yeah.
So this island migration is like an additional step, the additional computation and the combination.
Yeah, so the island migration is basically like a way to make the algorithm more parallel. So it's like you have some island here, which is a bunch of expressions. This sits on a CPU core, like a single CPU core, because it can really quickly run the evolution. You have another island on a different core, and they operate like completely independently of each other, which is really efficient because one can like go faster than the other if it needs to. Every so often, you have a migration period where you randomly select like a subset of each island and you swap them. And that's how you kind of combine their efforts.
So it kind of depends on the I/O of your hardware and so on.
Yeah.
Steps.
Yeah, so I've used it on like this one problem. We wanted like a really complex equation. So we used it on like 1,000 cores, and we had like 2,000 populations, and they're like all migrating like crazy. Okay, so it fit, and what we can do is if you run model, like if you just print the model, it's going to print all the equations. So it says like PyServerGrosser.equations. These are the different outputs, and these are their complexities and their losses. We can see the pick column. That is like the model it has currently selected as being the best, like the best trade-off. So we can do model.sympy, and this is going to get the sympy expression of the best equation. I don't know what the hell this is, but anyways. There's like another constant. Okay. So another thing we could do is, if you prefer a different expression, you can enter the index of the expression. So like say I want to look at the seventh equation here, then I can do model.sympy 7, and it'll give me the example. So yeah, and the other thing you can do is like, you can get a LaTeX version, like if you want to put it in a paper, you do model.latex, and it gives you like the LaTeX output. A bunch of features I wasted like way too much time on. You can also, so this is like the prediction. Like say you want to plot the output of an equation, you can do model.predict of x, or if you want to plot a specific equation, you give the number there. So like here, I want to plot the best model, the best equation, and then the second equation. You can see like the best equation is like almost perfect, and the simple equation, which is, what is the simple equation? It was the second. Okay, so it's like missing one of the terms, and the loss is obviously bad. Okay, any questions on that part? That's like just the API introduction. And so like the second time I run it, I mentioned it's gonna be much faster. So like if I rerun this, it should be like much faster. And that's just because like Julia is a just-in-time compiled language. The first time it runs, it's basically compiling it. The second time is gonna be faster. Yeah. So there it goes. It's almost done. And I think this time it found the correct equation. I mean, the first time it ran, there was like one constant, which is like 10 to the negative 8. I don't know. It's not a big deal. Okay. So let's move to the next part. Say that we are working on a specific subject where there's like a weird operator that nobody else uses, but I use in like my domain of biology. In this setting, like it doesn't really make sense to use like maybe like multiplication, division. Like maybe you actually want to use that operator because you find the equation that looks like your existing equations. So maybe you want to define like a custom operator. So here's how you do that. So say this is my data set, x0 to the 4th power minus 2. The way you define a custom operator is you literally just write it in the string. The syntax here is Julia syntax. So that's why we're doing like an explicit power here, as if you were writing LaTeX, not like the ** from Python. But the syntax is like mostly like Python. It's just some things are a little bit weird like that. That's how you define a custom operator. You also have to define it for SymPy to get a SymPy output. So here I define Court as just lambda x, so like a function which is x to the power of 4. When I do that, I define a custom operator, and it's going to compile it, put it in my package, and like run a search with that custom operator. And we can see if it works. Any questions about that? the nice part about this is like you could literally have like a long function, which is like branching logic or something, and it'll still work. And yeah, so it found something with the custom operator. So quart of x0 minus 2. That is the correct expression. And we can get the SymPy version, which, yeah. Okay, so some other notes. Yeah.
Yeah, so the custom, because so I can put any function I want in the custom.
Yeah.
So
Any binary or unary operator. So like 2 arguments or 1 argument.
Yeah, well, like something object based on like if statements or stuff like that. Or,
Something based on what?
like if statements or something like that.
X.
If
Oh, yeah.
It's smaller than.
Yeah. There is, so the if statement is like a bit weird. If I want to do an if statement, which I've actually done, I would write it like this. Equals, I think it's x greater than or equal to 0. And it's a ternary operator, which is like C, Y, or 0. So this is basically a statement. If x is greater than 0, y, otherwise 0. That lets you define if statements, and it'll use if statements in the genetic algorithm search, basically. There's some other like tiny details, like you actually technically have to do like templating shit, which is a bit annoying, but I have examples of this on the GitHub. But yeah, that part is a bit annoying, but like you can do if statements. Yeah.
Do you have an estimate on how much faster running this on Julia is compared to Python? Like whether it's worth the hassle?
So the fast part about this is like the really fast thing, which again I spent way too much time on, is I have it compile fused version of operators. So like say I have like a cosine and exponent, it's going to just in time compile cos of exponent of x and compile it with like simmed kernels, and it's going to be like fast as fuck. Like I literally spent like 6 months on this. There's a C package and it's like literally 10 times faster than the C package. Like it's a joke. Like there's another, if you want to like have a laugh, there's a package called gplearn, which is pure Python, and I don't know. I feel bad. I won't show it, but you could look up gplearn. The reason I wrote this is because like I want to use symbolic regression, but gplearn is like a piece of shit and it's so slow. So I wrote this, and I spent like 2 years of my life making it fast. Yeah.
So you mentioned like JIT compilation, right?
Yeah.
Like even libraries like JAX also provide kind of solutions in that way. So like, is this like something that you see like an alternative or?
Yeah. So I think JAX is more for static arrays, compiling functions on static arrays with static shapes. It's not good at tree-like algorithms. So actually someone wrote an implementation of DeepMind's AlphaGo, which is like a Monte Carlo tree search. It was literally like 100 times faster because I think JAX like can't compile the tree traversal step or something. Like I think for like the JAX, it compiles array operations, but it doesn't compile arbitrary code. So I think that's why you want to use like a language that is compiled for this. I do actually, another thing I spent way too long on is I have a JAX exporter. So you can model about JAX, and it'll give you like a JAX version of your equation. So then you can do the thing where like I want to replace my neural network by this function. And there's also PyTorch, which again, spent too long on. Yeah. Yeah.
Oh, no, I don't have a question.
Oh.
So when I look at this, like this tree, like this whole genetic algorithm, right?
Yeah.
I see kind of like two components. Like one is this discrete space of the tree itself, and also you have these coefficients which are in some sense continuous, right? So
yeah. So the way that works is there's actually two algorithms. So one is like this genetic algorithm, but actually one of the random genetic operators is a constant optimization module. So basically randomly it'll choose an equation, it'll take it out, and it'll run BFGS on it, which is a constant optimization algorithm. And it so it explicitly optimizes the constants, and that generally helps. Because like the genetic algorithm part is good for symbolic searches, but it's not good at like parameter fitting. So that's why you combine these two algorithms. Yeah. Yeah. Okay. So yeah, so we got the chord algorithm. Oh yeah, some other notes. I mentioned that complexity is technically just the number of nodes in the tree, but you can actually define custom complexities. So here you can define, like say, quartic is like a bit more complex than say square. So I could define quart as having complexity 2. And that's also a way of like punishing certain operators. Like maybe I want power law and square, but I don't want it to just do like power law of 2. So I can like punish it by making it cost more. I think that's it. Yeah. Questions about that? I can keep going. Okay. Oh yeah, if you're curious like how the scoring works, it's kind of like there's not a strong theory behind it. It's just something everybody in symbolic regression does. You basically look at the curve of complexity versus accuracy, and you look for a cliff. Wherever the cliff is like a good metric. That's like, oh, there's a cliff here, so this is probably a good equation. That's like literally how scoring works, and it's been done for a long time. It's really hard to understand why this works, and it doesn't work for everything, but it's like, it's a decent metric. Yeah.
Do you do that by like starting with a low complexity, doing one training run, and then?
So this scoring is just like a post-processing step.
Okay.
Like I don't use this in the search.
Okay.
I only use this after the search is completed, and I have these equations.
Okay.
Which one do I pick?
Okay, because.
But maybe I should do both. I don't know.
Yeah, so you're not incentivizing low complexity.
Yeah, in the search I am. The way I incentivize low complexity is I compute a histogram of the number of equations at every complexity, and it maybe looks like this, like there's more equations that are complex, and I invert this, and I go like this, so that if there's many equations with high complexity, those get punished. So it's like an adaptive parsimony.
And that's added to the fitness, or?
Yeah. So basically what you want is in any island, you want an equal number of equations at every complexity.
Okay. Yeah. We've done this with multi-objective optimization and then having the complexity as a second objective.
Yeah, I have, so yeah, I think, yeah, I've tried like normal parsimony too. And when I did my hyperparameter search and it just like turned into 0. I don't know. I think in, yeah, I don't know. I think it's also problem dependent.
Okay.
Yeah.
Is there a way to add the prior information?
Oh, yeah. So there's like a lot of work, especially in like program synthesis, which is like a generalization of symbolic regression to code. And there's a lot of work on defining complexity priors. It is like always arbitrary. And you say like, I want to have less equations at this complexity. I mean, it's like, it's pretty arbitrary, I think. Yeah. So, okay, here's a noise example. Let's say we have this equation, 5 cosine of 3.5x minus 1.3 plus noise. So the noise is epsilon. The noise is drawn from this distribution, which has a variable standard deviation. So every point has a different standard deviation. And basically for this problem, we're going to do a weighted mean squared error by the magnitude of the noise. So points which we measure very accurately, we're going to fit on them more than the more noisy points, basically. And for this problem, like you generally need more points. So we're going to fit 3,000 points here. And we're going to generate random noise between, what is it? Oh yeah, between 5 and 0.1 standard deviations. Yeah.
Go over that, because the minimum is still just if you are able to find a function that completely fits them, it's the same. It's the best function.
Wait, which point? This point?
The MSC, yeah.
Oh. Yeah.
The weighted MSC. So if you just go through all the points here, all the noisy points, you still get the best model according to the MSC.
Oh yeah, you could still overfit if that's what you mean. Yeah. Yeah, you can still overfit. Generally, like symbolic regression is it does not overfit as often as parameterized models. I think it's just less expressive. And it just doesn't seem to like overfit as often. So it's not really an issue.
So it doesn't matter the weighting that you have.
Yeah.
Yeah, it does matter. Like I know that's the likelihood.
Oh yeah, I think the weighting doesn't really matter.
Yeah,
actually.
The minimum is still the same.
Yeah, that's a good point. Yeah.
So.
Yeah, it shouldn't really matter.
Yeah. Okay.
Yeah. I just wanted to show you could use weights.
Okay.
Yeah. Yeah.
Kind of related to like voice point. Kind of have priors over like a generation process. You might need like a generator model of 3 cell cells, right? Like that would be kind of interesting to see. So.
Yeah, so there's a paper called Deep Symbolic Regressor where they learn a generative model over equations and they like update the latent parameter which describes that. It doesn't work that well in practice, but I think it's like an interesting direction. Yeah.
And another question is, I haven't read this Deep Symbolic Regressor paper, but like talking about like these mutation operators.
Yeah.
And that's kind of like a heuristic, right? Like there's no.
Oh yeah.
So
yeah, genetic like it's kind of dumb. Like you're just like you could brute force search it, but it's too inefficient. So you do like a bit better, but it's not like there's no like optimally. I think what you want is like some crazy reinforcement learning algorithm that tells you like what mutation operator to do, like some MCTS thing.
Yeah, have people like do that?
People have, but they haven't done it well. But I think it's an interesting direction. Yeah. It's also like such a like the optimization surface is like so disgusting. Like I think it's just really hard to fit neural networks on this type of problem. Some people do, but their models are like massive, and it's just like memorizing equations.
But I thought like your action space is not that huge. Like at every node
your conditioning space is massive. Like your action space is small because you're just choosing like what mutation, but the number of equations that could be like conditioning that reinforcement learning like algorithm are just insanely large.
Right, it's not
like the space of equations is really big. And you get completely different behavior. If you mutate like a multiplication into a division, then it could go from like smooth to like singularity. Like it's really disgusting space.
But I guess you also brought up this issue of like sparse reward. Like I thought like the reason why reinforcement learning is like so hard is because like, computing the reward is like kind of you're gonna get the reward like much later.
Yeah,
but
I don't know.
Yeah, you just have like.
I mean, people have tried it and it didn't work that well.
Okay, yeah.
Maybe that indicates it's hard. I don't know. Like I think it'd be interesting. Like if they get it working, it's probably good. Like the algorithm I use for choosing a mutation, you can look in the code. It's literally just like rand of like mutations. Like it's really dumb. And there's like weights which are constant. But I feel like you'd want to wait, like you'd want some algorithm to give you those. I think even like a little bit would help. Yeah.
Maybe it's also worth mentioning that like using the BFGS to optimize constants already introduces some gradient information, right?
Yeah.
And already is like is a benefit, right?
Yep.
It's worse without.
Yep. Yeah. Yeah. The BFGS is like really important. I think that's why GPLearn, the other Python one, doesn't work that well. It's because it just uses genetic operations on the constants.
Did you start out with introducing that, or like from the get-go?
No, I implemented it later, and it like helped. Like it made it work. Yeah. Yeah. Okay, so let's fit this data set. So this is 5 cosine 3.5 x 0 minus 1.3 plus noise. So let's plot this data set. It's pretty noisy, but like I feel like we could fit this. Like there's enough noise that if you like deconvolve this, it should be kind of smooth. So we do have weights, but like as Roy mentioned, maybe we don't need it.
It can make you choose other models that otherwise it wouldn't, because it doesn't penalize them as much. But the minimum is still the minimum.
Yeah, that's a good point. So here we're defining a custom loss too. So we're actually going to use, so in this example, I have like absolute, but you could do like squared error again. The way this works is X is the prediction, Y is the target, and W is the weight. This is any Julia code string, which is again similar to Python. I could also do like squared. And the default would also work. The default is a weighted error. So let's define custom loss. We're going to run it for 20 iterations, 20 populations of equations, and these operators. So let's fit it.
We are adding to a lot of constraints just by choosing which operators.
Yep. Yeah. I think generally the way to choose operators is maybe not based on like prediction power. It's based on what operators does your field use. Because like you want to get insights against existing models. So you want to use the same operators used in your field, I think. Because you want to see like similarities.
This could still model any function, but it would be very complex. So we're penalizing now for stuff that just uses the cosine.
Yeah. Yes, it's going to run. I think it already found it, so we can try stopping it early.
I had another question. Like,
yeah.
In the previous example, we had like this really small ball set, right? Like that's a 2.5 people per.
Yeah.
10 per. Like, why did BFGS not optimize that?
I think it tried to, but it's just like BFGS can't delete nodes. You can just set them to a really small value. And I think that's why it was still there. I mean, I think we might have just like ran it way too fast. I think you've run for like maybe like 1 second longer and it would have deleted it. I don't know. Yeah. Yeah, so I think it already found it. It's just like finishing it. Let me see. Coffee's at 3, right? Okay. So let's see if we can get to this. So the last example is it's a neural net combined with symbolic regression. Here we're actually going to interpret a neural network with symbolic regression. So the problem is as follows. This is our learned model. We have a time series xi, a learned function g, and a learned function f. And so this is basically like summing a function evaluated on every time step. So G is like, maybe it takes the coordinates and does a coordinate transform. And then we just sum that over the time series. And we pass the summed value to F. The true model is this. This is the true model. So the true coordinate transform is xi0 squared plus 6 cos 2x2. This gets summed, and then we square it. So like F should recover the square. G should recover this. And so this is kind of a way of using symbolic regression on like different types of data structures. You use the neural net to break it down into kernels that you can then interpret. Like traditionally, this would be really hard for symbolic regression because the equation space gets squared and you have like the squared number of possibilities. But the neural net, like the neural net step is really fast. So you've broken the problem into pieces, basically.
So you do it like layer by layer?
We don't do it layer by layer, we do it function by function. So in this case, we have two functions, which are both neural networks, multi-layer neural networks. So G is like a multi-layer perceptron. And so is F. It's basically latent space by latent space, not every single hidden layer. You have defined latent spaces. If that makes sense.
But how did you come to this form though? Like, you know, okay, in this case, you know that it has this structure.
Yeah.
But like generally, I'm just fitting like a neural net.
Yeah, generally, like this is a really deep question. Like, what is the correct inductive bias? What is the correct architecture for a problem? I think a metric that you found a good architecture is that you'll find a sparse G. Like you found a simple model within your architecture. And that's like a good metric, but there's no way to know, like going into a problem, what it is, unless you know something about the physics, maybe. Yeah.
Well, we agreed that outcome tracer wasn't true.
Yeah, I mean, you gotta make some assumptions to not hate yourself, I guess. Okay, I think our noise model finished, so we can see if we found the true equation. And you can see, because it's noisy, like there's going to be other equations that are just fit to noise. But this score that is like the cliff thing, like the score has found the correct one. So let's plot this. So this is like the SymPy version, which is correct. And let's plot it. And so yeah, looks pretty nice. And we have the symbolic form. Okay, so yeah, we're gonna run out of time definitely. So let's just, I'll just like describe this and we can run it in the background. So we're gonna generate 10,000 examples of this time series. And we're going to define a neural network. So this is PyTorch. And I unfortunately do not have a time to give like a detailed PyTorch tutorial. But I'll give you like maybe a little bit of intuition. And I'm sure like many of you have used PyTorch. So maybe you can help your friends kind of understand it if you have time. Basically, this here is a definition of a neural network. This is a linear layer. Every time you write nn.linear, you are you're basically doing like one layer of a neural net. So you can see like that is one layer, and then I am doing the activations afterwards. And then I do another layer, another activations. So that's how you define just like a basic neural network in PyTorch. Is like this nn.sequential, which basically means like a bunch of things stacked on each other. The two numbers you need to pay attention to are the input size. This is how many features are going in, and the size out, which is how many features go out of the neural net. The hidden is how many like nodes are in the middle. So if you have more nodes, it's going to be more expressive, but it's more expensive. So in this model, I mentioned we want to define two functions, f and g, in this expression. So in our network, which I'm going to call SumNet, I'm going to define G is MLP, 5 inputs, 1 output. F is MLP, 1 input, 1 output. So it's functions from R to R and R5 to R. The forward model runs G on the input features. Then it does a summation over the time dimension, and then it runs F on the output. So that's pretty much like all you need to do to configure a PyTorch model. It's just this. PyTorch kind of takes care of the rest. So in this example, we're using PyTorch Lightning, which is it's a nice like helper library to run the training for you, so you don't have to worry about it. Basically, I just defined the optimizer here, which is like what algorithm is going to tune the parameters. I define my loss. I'm going to say mean squared error loss. You can literally just copy these for most problems. I'm going to define the network. This is just like moving the data into PyTorch. Do that. And then in PyTorch, I basically I stick my model into this thing, PyTorch lightning.trainer, and then I do trainer.fit. Yeah, I don't have, sorry, I don't have time to go into like more details, but there's lots of good tutorials on like PyTorch Lightning, and I think we might have someone talk about PyTorch next week too. Yeah.
I'm not sure if I understand it. So is the reason you're like using this two-step strategy of first doing an NLP and then symbolically regressing that kind of attract the MLP gradient information, and then afterwards just regress the individual NLPs?
Yeah.
Well, that's like the reason.
Exactly. Yeah, you want to. So you wrote your model in this form, so you know that whatever function you fit to xij z pairs is going to look like this. Then you basically take this learn function g, you rip it out, and you fit it with symbolic regression.
Okay.
And then you do the same with f.
Okay.
Then once you have those analytic expressions, you put them inside that equation. So there's going to be like this summation in your equation that you don't have to like fit. It's already there.
So you could like also throw symbolic regression just directly on the double expression, but it would be very complicated.
Exactly. Yeah. So you basically, if you want to fit symbolic regression directly here, you've squared the number of equations. So now you have to fit like the space of f times the space of g.
Okay.
So it's much too complex.
I see.
Yeah. Yeah. So yeah, it's going to train for a bit. And then the rest of it is like, here's how you extract function g with Python. Okay, so it's coffee time, so we can get caffeinated. Okay, thanks everyone. Happy to answer questions after too. Yeah.
Let's take it away.
So thanks very much. Very happy to be here to discuss about this topic. The interesting thing about mathematics for deep network is that mostly we don't understand. There are many approaches, many tools, so it's a very good topic for research for whoever has a mathematical background. Whereas you have tens of thousands of papers on applied deep networks, new data analysis algorithms, and so on. On the mathematical interface, there is much less, despite the fact that really the problem is largely open. So what I'll try today is to give you some hints of the type of approaches that one can take to look at this kind of problem. So I'll be looking at the two sides of machine learning. On one side, you have the unsupervised learning problems, where what you want is, given a set of data that are right here, xi, you'd like to estimate the probability distribution of this data. And interesting applications are in particular in physics, but also in, for generating all types of signals. The interesting things about physics is that we do have models of data. So one can check a posteriori, whereas these models that you've been introducing through these deep networks are relevant or not. So these are examples of physical fields on the left coming from cosmology, mass density. On the right, you have turbulences of fluid, liquid or gas, again, here in astrophysics. Now let's see down. And then you have the second side of the world of machine learning, which is classification, estimations. So here you want to estimate a y given the x, and you have your data set to do so. So example of xi and yi. Image classification, of course, has been the domain where deep network has shown incredible performance, but also many other fields, in particular, again, in physics. Quantum energy regression is an example that I may have time to speak about. So deep neural networks, you all know basically what they are about. I put here the name of Yann Lequin, not only because he gave this talk, but he wrote something really very important to this topic, which is structure. Instead of having fully connected deep neural network, which essentially doesn't learn or are very hard to learn, he introduced structure. And how did he introduce structure? Through these ideas of convolution. The fact that typically when you have an object which translates, it's not going to change its nature. So you want the filters that are going to be used by the network to be translation covariant and therefore convolutions. So you have these convolutions. This is the convolution filters followed by a nonlinearity. Here I took a ReLU as it is often used. And then you have the next layers with many layers, many channels within your layer. And each channel is going to be convolved with a filter. All this is going to be summed up to give you one response. And you'll have different filters corresponding to the different channels of the next layer, and so on. And progressively, when you look at these networks, one of the things which disappear is space. Initially, the image is entirely indexed by space. At the end, space has essentially totally disappeared. And it disappears progressively through this progressive subsampling until the last layer where you have this linear aggregation to do your prediction. So basically, it's about learning a set of parameters, which is huge, typically can grow to several billions from the data by minimizing some loss. And the big surprise, as you know, is that not only got remarkable results on classification of images, but also kind of data, sounds, language, regression in physics, all kind of signal and image generation, which means that there is something totally generic behind that. We are not speaking about specifically images, audio, or something. There's something common between all these type of problems. And the issue from a mathematical standpoint is to understand what is common. How come all these problems can be tackled with a similar architecture, which is the one which is shown over there. So question is how to interpret this architecture. So there is an idea of multi-scale in the sense that you see that initially your filters are looking in a very small neighborhood. But as you subsample, the coefficients here depends on the whole image. So progressively you aggregate the information as you go deeper and deeper. So what's really the role of the filters, of the nonlinearities, and what kind of mathematics can we use to tackle these kind of problems? The difficulty on the mathematical side is that it covers a very broad range of mathematics. Probability statistics, obviously, but also optimization, harmonic analysis, group theory, and you see all these tools which are around. question is how to think globally about the problem. When are these tools coming as an important element? So if you look also empirically, at least at the first layer, you observe the filters are not very complicated. The filters at the first layers, these are obtained from one of the first deep network, but they're almost always the same. You see these little waves, very localized on the first layer, almost more or less the same, and you see the equivalent thing on audio and different type of things. Then it gets more complicated because you aggregate all these filters, so the interpretations of the filters afterwards gets very difficult. Okay, so what I'd like to present is two sides. First of all, what's the role of prior in this problem? We know very well that we can't learn without prior. In this kind of architecture, where is the prior? And I'm going to proceed, instead of beginning from architectures which are complicated, I'm going to proceed from first principle, looking at the problem and progressively construct architectures as a function of the type of prior information I have. And I'll show in what sense the two simple architectures are failing and in what sense do we need to continue. So one of the very important concepts, of course, behind all that is the famous curse of dimensionality. In very high dimension, you cannot learn. It's too complex. So the only reason why you may have a hope to solve a problem is because there is structure and because you've been able to incorporate some of this structure within your algorithm, here the architecture. I'll show that the need of probability is almost automatic. The fact that you are in high dimension forces you to have a probabilistic look at the problem, and I'll show why it's really so important, in particular because you have concentration phenomena. And regularity. As I said, the only reason why you can learn is that there is some form of simplicity. This form of simplicity, you should be able to express it as some form of mathematical regularity, and wavelet will be one tool to do so. In the second part, I'll look more, or the last part, the third, the two-third, at the problems of interaction across scale. And the first part, I'll try to do as much as I can without learning, or just learning the last time. Then we'll see why learning is really necessary. And in one sense, the learning is really opening many unsolved problems. So that will be the program for today. So let me begin with the curse of dimensionality, which I suppose you all know very well about. Suppose you indeed want to estimate a function, a y given an x, so a certain function f of x, and you have examples. If you look at the problem, it looks very easy because after all, it's just a problem of interpolation. You have different value xi, you know the value of your function yi at the different xi, and these are shown by the different colors. Now you have a new x, you want to compute the value of f of x. The only thing you have to do is, in some sense, interpolate your function by using some form of regularity. Now, why this never works naively in high dimension? The problems is that if you pick an x, all the examples will be very far away in your space. And to get an intuition for that, suppose you are in 2D that you want to ensure that all points have an example at a distance epsilon. Then what you need is to uniformly sample your 2D space, and you will need epsilon to the power minus d point. Now, if you are in dimension d, in other words, if the number of parameter x is d, the number of points that you will need will be greater than epsilon to the power minus d. Now, just to check, if you take for epsilon 1/10, which is not so big, if you take for d 80, you have 10 to the power 80, which is already more than the number of atoms in the universe. So it's hopeless. And dimension 80 is very small. An image is of dimension 1 million. So how can you go about solving this problem? First of all, this tells you most functions, you won't be able to learn them. The only functions that you'll be able to learn are somewhere functions which are extremely regular on your high dimensional space. So very strong regularity. Question is, what kind of regularity can these functions have? And that's the core of the mathematics in this field. Okay, so the first kind of idea that comes to mind is to use notions of symmetries, invariance. So that comes typically very much used in physics. So suppose that you want to know whether X is in class Y1 or in class 2. So in other words, you want to identify the set of all X, such as f of X is equal to Y, this level set. Now, we'll say that there is a symmetry if these sets do not change when you transform X by some transformation G. In other words, if you have a red point, you transform it by your transformation G, it stays a red point. So the class doesn't change. Example, translation. You take, for example, an iPhone, I translate it, it's still an iPhone. So the class of iPhone is invariant to translation. So in what sense is that useful? So observe that the set of all transformation that is going to preserve the value of F is what is called a group, in the sense that if you compose two symmetry, because F is invariant to G1, it's still going to be F of G2 applied to X, and it's invariant to G2, so it's going to be F of X. In other words, the composition of two symmetries remains a symmetry, so you have what is called a group structure. Now, why is that useful? It's useful because basically what it tells you is that you only need to learn the space or the set omega y up to the transformation G. So if you're not interested to translation, basically you can kill the translation parameters, and that's going to reduce the number of parameters. The problem is how many parameters you're going to reduce. Well, it's going to correspond to the dimension of the group. In other words, the number of parameters to specify the transformation. So once this observation is done, and that's a very classic observation in machine learning, obviously the questions are, what are the kind of symmetry that you can take advantage of? So in images, if you want to recognize digits here, typically the problem, as I mentioned initially, is invariant to translation. So the group that you have here will be the translation group, the set of all possible tau, such as X is transformed by tau, where tau is a constant for now. Now, that's nice, but it doesn't bring you much. Why? Because the translation has two parameters. So you go from a space of dimension 1 million to 1 million minus 2. Big deal. It didn't bring much. So what you need are symmetries which are much, much bigger. Now, in terms of geometry, the symmetries which are much bigger are deformations. If you take an image as this one, as long as the deformation is small, you can recognize essentially the same painting. When the deformation is too big, the painting is changing. Why deformation are natural? Because they are also very natural in physics. When you have a turbulent fluid, it's typically going to evolve through deformations because you have transport phenomena of mass, of particles, and so on. So being able to be invariant to small deformation, the advantage is that if you know that this property is true, it's defined by much more parameters, so you may be able to kill more information. Now, this is not enough. Initially, many people, including myself, thought, okay, that's the angle to attack the problem, and we did, and we moved a bit along. But by doing that, you're not able to reduce dimension up to what typically neural net is able to do recognition. Now, to understand that, I'm going to ask a very naive question. Is it more difficult, very badly posed question, by the way, is it more difficult to estimate the class y from X in RD when D increase, or it's simpler? If you follow the logic that I gave, which is to say, well, all this is a problem of interpolation. So what you want is to approximate a function f of x. well, then X belongs to a cube, let's say 0, 1 in dimension D. So if D increase, the number of parameters that is going to define F is much bigger. So typically it's going to be more difficult, and you have your curse of dimensionality. And as I said, to try to face that kind of problem, you may try to find some source of regularity of F. And there has been a lot of research at the interface of harmonic analysis, functional analysis, and machine learning, trying to define functional spaces which had that type of regularity. And basically, it's a failure. It's a failure. The first theorem you have out of that is the universal approximation theorem, which tells you that from a one-layer network, you can approximate any function which has a finite energy. Big deal, because the number of neurons that you need explodes exponentially with a dimension. So it's essentially unusable mathematics. To have something which is usable, you need to have bounds. You need to know that the number of neurons is not going to grow too fast when the dimension increases. Now you have a totally different point of view, which is usually the point of view that engineers will take, or people developing algorithms, which is a more probabilistic point of view. The difference is subtle but important. Instead of looking at the value of function at different points, we're going to look at the function horizontally. So for a fixed y, I'm going to look at all the x, such as f of x is equal to y. In other words, I'm going to look at the level set of my function. And what typically a probabilistic model would do is to try to define a notion of probability and try to find a y such that the probability of y given x is maximum. Why is that related to these horizontal lines? Because if you apply the base formula, this is the same that the probability of x given y multiplied by the probability of the class, which may be constant across all class, and divided by p of x, which you don't care because you want to find the y which maximizes that. Now, what is p of x given y? It's basically the size, the measure of the set of all point x such as f of x equal to 1. In other words, it's the measure of all the points which is along this line. So what you are there looking suddenly is at something very different. You're looking at the way your data concentrate. You don't suppose anymore that the data is in 0, 1 or d. You rather try to understand where the data is going to be spread in the space. And the fact is, when you have more data, you will typically be able to average more coefficient and exhibit concentration phenomena, which comes from the law of large number. And there the mathematical tools are totally different. The answer in this framework is no, obviously it's easier because you have the more data to answer your question. If you have an image, if you have a better resolution image, obviously you should be able to recognize things better. It shouldn't be more difficult. And in this case, the tools are from probability. And we'll see that at the end of the day, it's a mix of these 2 points of view that allows to move on. Okay, if you take the second path, there is one paper which basically has set the domain, which is a paper by Fisher, published exactly 100 years ago, called On the Mathematical Foundation of Theoretical Physics. It's on the web. I really recommend to get this paper. It's amazing to get a paper which is still relevant, which basically sets the program on which we are still all working. It basically sets all the basis of including what people are doing on these machine learning algorithms. So the problem, the way it was set by Fisher, to say, okay, we're going to model the data, xi, as samples of a probability distribution. And I'm going to try to approximate this probability distribution with a probability distribution which is parameterized, p theta, and the best approximation will be p theta star. Now, he introduced the notion of maximum likelihood. So this notion is very intuitive. If you have a parameter theta, and you want to represent your, at best, your data, what you'd like to do is to find a parameter theta such that the probability of X is maximum. In other words, that your data, if you observe this data, it's probably because this data was very likely to appear. And therefore, you want to find the theta which maximizes this probability. Now, because the data is here supposed to be independent, the probability of X is the product of the probability of all Xi. Okay, I suppose here that they are independent and same probability. So what you see here is that you have a separable structure. Because you have this separable structure, if you take the log, you get what is called the log likelihood. Here, I will take a minus so that the maximum likelihood corresponds to a minimization of the loss. I divide by 1/n, the log of this probability. It's a product, it's going to be the sum of the log. And what you get is a mean. And this mean, that's the law of large number, tells you that it's going to concentrate to the expected value. So the remarkable point is that when you have these separability structures, you have, through averaging phenomena, through averaging technique, concentrations of your values. Another way to express that, which is typically the way it's expressed often in machine learning, is to rather look at the Kullback-Leibler distance, or it's also called the cross entropy between P and P theta. This is always positive. It's 0 if and only if P theta equal P, and it will be the integral of P of X log of P divided by P theta. And what you see appearing here as a first term is precisely this maximum likelihood. And you have a second term, which is the entropy. So minimizing the maximum likelihood is the same thing than minimizing the cross entropy or the Kullback-Leibler distance. And this is what essentially all the algorithms are doing at the end of deep networks. Yes.
Yeah, but this concentration is as n goes to infinity, right? Like,
yeah.
That concentration was as d goes to infinity, like the one on the previous.
Exactly. You're absolutely right. Here it's when n goes to infinity. Now, in what sense is that showing the way? The way classical statistics is d small n goes to infinity. Is that then within d, you are going to begin to look at structure which are independent. So that within d, you can average and you can get some separability. Here, the separability is given to you. We are told if this data is independent. Then you'll have to get your image or your structure and find what is independent and average. And that's what corresponds to the pooling. But the pooling has to be very subtle so that you average things of the same nature. Thanks for that important question. Okay, next step, what's the relation with optimization? Of course, what you need is to minimize this log likelihood. So the standard algorithms to do that is to do a gradient descent. Now, if you do a gradient descent, so here's theta of t plus 1 is theta t minus, you go in the direction of the negative gradient, the convergence is going to be controlled by the Hessian here. The Hessian is the matrix of the second derivatives, okay? And at the minimum, this Hessian matrix corresponds to the notion of future information, which will give you the precision that you can access for the estimation. That was already introduced in the 1922 paper. Now, theorem that you probably all know very well is that if you then begin to do a gradient descent, if you are in the good case, which is that you have a convex phenomena, the convergence is going to be controlled by the eigenvalue of the Hessian. And what you will need is that the learning rate, in other words, the alpha here has to be smaller than 1 over the largest eigenvalue. And you will also need the small eigenvalues to move on so that the convergence is essentially, in that case, going to be exponential, but that's going to depend upon the ratio between the smallest and the largest eigenvalue. And typically, a badly conditioned situation is when you have a very big largest eigenvalue
and a very smallest eigenvalue here, the curvature is very small. So the algorithm will have to move slowly because it's driven by the biggest eigenvalue. It will move like that, and it will take forever to move in that direction, okay?
Very classic problem. So one of the major issue in that kind of situation
Is to have a well-conditioned algorithm. And we all know you've probably been waiting for days and days for your algorithms to converge. This is a major issue. If you're not working at Google, you may never be able to learn. So these are central topics.
But you see that these topics are directly related to the issue of representation, because here we are speaking about understanding the nature of this linear operator.
I'm going to take a simple but yet very rich example, which is the family
of the exponential models, which is basically used mostly all over statistical physics. So here, the p theta is going to be a function of, the energy here is linear in the parameters. So u of x in physics will be called the potential. Theta will be the parameters are called sometimes the coupling parameters, what defines the interactions. So theta is a vector, u is a vector, so it's typically the sum of theta k uk. And the problem is to find the parameters.
So in this case, because the problem is linear,
you can verify that it is indeed convex. You can compute the gradient. This is a direct computation that I'll let you do. And you can verify the gradient of the likelihood is just going to be the difference between the average value of the potential for the true probability minus the average value of the potential for the probability that you are progressively updating and estimating.
So basically, setting this gradient to 0 amounts to find a probability distribution which has the same moment, same probability distribution, and that's your update with the gradient descent.
Now, in this case, you can
compute analytically the Hessian and verify that the Hessian is nothing but the covariance matrix of these u of x. So the whole problem, you know that it's a covariance, so it's positive, but it has to be well conditioned.
Okay, so let's look at more interesting problems or real problems.
So here is a set of physical problems.
On the left, you have 5-4. It's an example which corresponds to the simplest example where you have a phase transition phenomena. This is cosmological example and turbulence. So in this problem,
what you'd like, as I said, is to estimate this E of x. And what I'll try to show is why
naturally we're going to move to something deep. So you have three problems here. The first problem
is to define models from priors. And I propose here to define a model for now, which just is going to be a linear function of this u of x. So the problem will be what kind of u of x can learn all these type of problems. Can you make sure that you learn theta fast? And of course, in that case, you also
would like to sample your problem. So that will be the first set of problems, and then we'll move to supervise.
So first thing you may think, and what everybody has been thinking
in probability is, let's try Gaussian model, okay? These are turbulence. Kolmogorov in 1942 proposed a Gaussian model of turbulence. So what does it mean? It's stationary. The fact that it's stationary means that the probability distribution doesn't change when x is translated, invariant to the translation. A Gaussian model, that means that you have your probability is defined by the inverse of the covariance matrix here and the mean of x. So it's basically a bilinear form. In other words, the energy has a quadratic form. So here's the parameters, the mean and the covariance. If you know
that x is stationary, then you know that k is a convolution. Toeplitz matrix, okay? So
that goes into your prior information.
If you know that k is a convolution, then you know how to diagonalize. You go in the Fourier basis, and the eigenvalues will be the Fourier transform of K. And if you pick these kind of images, or you pick essentially any type of image, face and so on, you look at the eigenvalue of the covariance, they have a power law decay. Typically, eta is equal to 1 for images. What's the problem? These are the eigenvalue, the covariance. And the ratio between the largest and the smallest eigenvalue is huge.
So if you naively try to apply your gradient descent on that, it will take forever.
And here came ideas. And what I'm going to try to show a bit through this talk is that machine learning and deep network is a new field with very new ideas. But the theoretical basis comes from everywhere, in mathematics, but also in physics. And here, there is this idea, which was very fundamental, for which Wilson got the Nobel Prize in the 70s, which is this idea of renormalization. The idea is to say, if you look at a very complicated physical phenomenon, one way to simplify the analysis is to look at the evolution across scale. So you look at the same phenomena and you coarsen it progressively, like that. And you renormalize it so that the amplitude looks the same. If you coarsen your phenomena, you are going to reduce the number of degrees of freedom of the problem. Okay? So it should be, in some sense, easier to estimate the probability distribution because you are in a smaller space. So now you can try to compute the probability distribution of this image at the coarser scale. And same thing, try to build a model with your potential energy. And the beautiful idea of Wilson was to say, well, but what we're going to look is the evolution of the parameter from theta j to theta j minus 1. Yes.
Are these like the coupling constants in an Ising Hamiltonian?
That's exactly the coupling constant. The theta are exactly the coupling constant.
Okay.
And in an Ising model, that's the closest to an Ising model, but with a continuous function. You will look at the evolution of the coupling constants across scale.
And add the phase transition, and you can view that as a dynamical system. And this dynamical system may have a fixed point.
And this fixed point is exactly at the phase transition, when gas gets to be ice or transform it to water and so on. And the interesting thing is that at this point, which looks very complicated, in some sense, the system is the simplest because the constant which drives the phenomena across scale is totally regular.
So the idea is to look for regularity, but look for regularity across scale. Now, how is this related to DeepNet? How can we incorporate that into DeepNet? That's what I'm going now to show.
So the whole idea that comes from here is to say we want to understand the regularity. And we want to build a model of X0, but we can begin from a model of a very small image and then progressively
try to understand from coarse to fine the evolution of this model. Now, what is going to be key? If I have a model of the very coarse image, what I need is to understand what's the probability distribution of the finer scale image given the coarser scale image. So what I need is to compute this transition probability, okay?
And of course, I can factorize it. I can say that the probability of X0 is just the probability of the coarser scale and then multiply by the transition like a Markov chain. But I'm doing here the Markov chain
across scales. Okay, but how can you put that in a network?
So if you look at the two quantities,
you have your image at the fine scale and the image at the coarser scale. To go reverse, what you need is to have the complement of information, the degrees of freedom that you've lost. You have to introduce them in order to come back to xj minus 1. And that's what these wavelet orthogonal coefficients will give you.
Intuitively, what has disappeared from here to here? It's the high frequency. It's the quickly varying structures of the image,
okay? That's what you need to represent. So how can you do that?
and that was the work that was done in the 90s and early 2000s, is to observe that you can build an orthogonal basis. Yes?
Sorry, doesn't this really depend on how you course it at that point? Like
Yes. For any kind of way to filter, you can find an orthogonal basis by doing the orthogonal complement. But you're right that each time the basis will depend upon the courses. So if you do a block averaging, it will be called a Haar basis. If you do an averaging which is more subtle, more regular, you'll get other type of wavelet basis. Absolutely right. So these wavelets, they look like the filters I showed you on the first slide of the first layer of AlexNet. Small, locally oscillating waveform. What are these going to do? Basically, they are going to extract the variation of your image at very high frequencies in different directions. There is almost no structure in this case because this is a simpler image. I'll show examples which are obviously more complicated. But basically, once you have this and this, you can come back to here. And these coefficients, how can you express them? Basically as a convolution and a subsampling. So we begin to have these kind of ideas. Now, this one image, you need to sub-decompose. Oh, sorry. The probability that I was interested, which is the transition probability, since xj minus 1 is given by xj bar and xj, this is the same thing than predicting the high frequencies from the low frequency. So the problem will be each time to predict this from this. But this, I'm going to sub-decompose it. At the next scale, So let me show an example. This is a bigger image, more structured. This is the Fourier domain. So these are the low frequency where lives all the frequencies corresponding to this. What basically we're doing is splitting this image into a lower frequency image. This corresponds to the lower frequency square. And these three images, which are the wavelet coefficients, they give you the variation along horizontal vertical corners. You see the edge, gray means 0 values. This is the filtering and subsampling structure, and you get that. Now you take this image, you split it. In the Fourier domain, you've been splitting again the Fourier domain. You have this image, you split it, and you split it, okay? That's an orthogonal transform. If you take something more complicated, here you get, what you see is all the information is concentrated near the edge. Most points are gray, nearly 0. Very strong dependency across scale. It's going to be very important to understand how the information evolves across scale or across orientations. Okay, so how can you rewrite this problem to get close? What we basically thought is that the conditional probability, I can view them as computing the probability of the wavelet coefficients, the X bar, the fluctuations, given the low frequencies. So now, instead of building a model of the whole image, I have a much simpler problem. I just want to build a model of the high frequencies, supposing that I know all the low frequency structures. These are the conditional probability. Basically, you'll do the following. You build a model, very coarse scale, Gaussian process, typically because you've been averaging very much. You first build a model of the high frequency given xj, and then you recombine that to get the higher resolution image. You then build a model of your higher frequencies given that, and you build the next scale. So why this is simpler? Because you basically took a very complex probability, you factorize it in terms which are simpler. Why? These terms are much more Gaussian, much simpler, much more local than the original probability. We'll see that this is well conditioned. You don't have the problem of conditioning initially, and you can have a fast sample. I'm not saying the problem is trivial. This can become complicated, and we'll see that the whole problem is to build a model of these objects, which was the core intuition and tools that physicists have been using since the 70s. So how do you do that? Well, if you have a model
what you need is basically to estimate the parameters of your model here. And to do that, you're going to do a gradient descent. The problem of the gradient descent, I said, is that the Haitian may be badly conditioned. Why this is not going to happen here? This is not going to happen because here are your eigenvalues. They decay in the Fourier domain exponentially like that. But what did you do? You've been splitting the frequency interval. I showed it in 2D, but in 1D, this is the wavelet at one scale. They cover this high frequency. Next scale, next scale. So if you pick one particular scale, let's say this one, the eigenvalues, they don't vary much anymore. So within the frequency band, within one scale, the condition number of your Haitian is not going to be bad anymore. And because you renormalize, that means you put everybody at the same level, the weighted coefficient looks like white noise. Not automatically Gaussian white noise, but white noise. And the condition number is going to be good, and you're going to get a fast convergence. Okay, so just to illustrate, this is the simplest example. That's the equivalent of Ising-Mont. Beta is the temperature. This is an example in physics where you have a Gaussian term, which is here, and you have what is called a potential term. What is the potential term? It's here. It forces the pixel of the image either to be equal to -1 or 1, preferably, by having the energy lower, okay? And when you increase temperature, suddenly you see this phase transition where everybody is correlated with everybody, very long range correlation at a critical temperature. Now, if you put yourself at critical temperature, it's a nightmare in terms of computations, unless, and that's shown by the speed of convergence of the gradient descent when the temperature reaches the critical temperature. The number of iterations gets very long. If you separate the scale and you renormalize, everything converges quickly, independently from this temperature, because you kill this bad condition. So that's the relation with optimization. In this case, everything works well because it's a toy problem. You know very well how the energy looks like. If you look and you can approximate your potential with a ReLU, that will be the role of the nonlinearity in the network. If you move to more complicated problem, it doesn't work. So I'm first going to show where it works. This is the simplest cosmological problem where it's called problem of weak lensing. Basically, these are images of density with very intense points corresponding to forward objects such as galaxies and things like that. You want to model this probability distribution. This is a real problem because there is a multi-billion-dollar satellite that is going to be sent in Europe called Euclidean mission, and you want to model the statistics of these things. So for relatively simple images like that, you can build a model with a Gaussian terms plus a scalar potential and resynthesize images with quick algorithms. But, before the but, yeah, but it doesn't work for more complicated geometric structures. Before this but, let me show you the relation with deep. What did we do? We took an image, divided at different scale like that with convolution subsampling, and built a potential in a filter across, which basically gives the information about covariance and scalar potential. The but is that this is not sufficiently rich. It's a very simple network to capture geometries. And if you look at an image such as this one, these are the wavelet coefficients. You can see that the wavelet coefficients, they don't look like Gaussian white noise. They are very structured. They are sparse, but very structured when you compute them. And what you really want to understand is the conditional probability. So you need to build stronger models. And that's where nonlinearities are going to become much more important. So the goal here again is get this structure, understand how these things are dependent, capture these conditional probabilities. Okay, that's the last part of the talk. So our goal is to build models which relates the information across scale. Yes.
I didn't understand the role of the nonlinearity in this multi-scale view.
The role of the nonlinearity, you're right, I went very fast, is in modeling the potential. The potential, we can write it as make a piecewise linear approximation that we have to learn. And this piecewise linear approximation, we model it with a sum of ReLU. A sum of one-dimensional ReLU, you can get a piecewise linear approximation. But I'm going to show here that the nonlinearity has other much more important goals. That was the first glimpse of the role of a nonlinearity. Here, the whole idea is to understand how to construct these models that can be linearly to get a linear model. So, different way to react. You want to go beyond Gaussian. The first reaction of most mathematicians, physicians, is to say, okay, you limited yourself to second order moments. Why not going to third, fourth order, fifth order moments? And that's what everybody tried in between the 2008, the 1980s and 2010, basically. For 30 years, people have been trying to use high order moments. And that was a failure. Why is it a failure? Because you have much too many high order moments. And when you estimate these moments, they have a very high variance. So sometimes there are a few applications, but it's not able to describe complex fields such as turbulence, phases, or things like that. Okay, so it doesn't work. What about learning this with a convolution network? That works. And we've seen these generative networks, which are very powerful. However, we don't understand the nature. What I'd like to show is that as long as the field is, the image is stationary ergonomic, you don't need to worry. We have enough prior information. The day you begin to have structure and basically you need to have memory, you will need to learn. And that will be the last part that I'll be showing. So let me begin with problems which are still quite complicated, such as turbulence. There is geometry, but you have something which is invariant to translation, which is stationary. What is the first idea that comes to mind if you are asked to relate the coefficient at different scale? It would be, well, let's just compute the correlations between these coefficients. The problem is the correlation will always be zero. That's an exercise to do. Why? Because these coefficients are obtained by a convolution of the data with a filter. And when you look at different scale, the filters have frequency which don't have a line. In other words, if you look at the image, they are going to oscillate. And the phase, it's not going to be in phase. And because of the phase oscillation, the correlation is going to be zero. But you can prove it, it's an exercise. You write the expected value as the integral of, you apply Parseval theorem, and you'll get a zero. Okay, how to go around that? You have to kill the phase. You have to kill the oscillation. Rectifier will do the job. Another way to do it, which is simpler from a mathematical point of view, is just to take the modulus, the absolute value of this is complex, the modulus. If you take the modulus, clearly this correlation will be non-zero. In fact, the covariance is going to be non-zero. And the modulus with the one which keeps the phase, these are going to be non-zero. So where is here the first role of the nonlinearity is to create correlations between structure which are not correlated because they oscillate at different frequency. And that's what will allow to understand how things, the information propagates across scales. So then, of course, the whole problem of this kind of naive correlation is you get huge correlation matrices because for any translation tau, you have covariance. What you want is to reduce the number of coefficients. So you would like to almost diagonalize these things. And what you can show is to do that, you have to do, again, a frequency binning for the one who are thinking in terms of physics. In other words, again, you need to, after doing the nonlinearity, do again the filtering. And if you filter at different frequencies, you keep these coefficients, which are again applying a new way that transform. You can almost diagonalize the covariance. So basically, the idea is we are moving towards an algorithm which spread with filters, apply a nonlinearity to make sure that you are going to have non-zero correlation, and again, filter. So if I look at it that way, this was the first wavelet transform that I did. I'm going to apply a modulus and also a skip connection in this case. I won't go into, well, the skip connection, sorry, I can explain where it comes from. It comes from the fact that I also need to correlate the value with the phase and without the phase. So I need to propagate this information and correlate it, and that will be the role of the skip connection. So that's the nonlinearity and the skip connection. I redo a wavelet transform, and then I normalize everything so that everything, that's the batch normalization. Batch normalization is what people in physics call normalization in the normalization group. And then I compute the covariance at each scale, and I build my model. This begins to look like a deep net. I spread, I look at the information across scale, but I don't learn anything because all the information is in the prior. I have enough information about the physics of the problem. If you do that, these are the models that you obtain. These were the original image. You can do the same thing, in fact, with a deep net. For example, people have been doing that by learning a deep net with ImageNet and doing texture synthesis from the learned deep net. The only difference is that here you need less than 1,000 coefficients. With a deep net, you need about 100,000 coefficients because you do it in a brute force way. These are images that are synthesized from the models. In other words, progressively from the coarse to fine scale. And you can see that in this case, you did reproduce the structure. If you put a lot of coefficients, you can even reproduce things like this kind of texture. But here we begin to have so many coefficients because here I think we need 30,000 coefficients. Compared to an image of 200,000, you begin to do overfitting. That's the issue when you learn with too many coefficients. And the next stage is learning. So one question is, from this kind of representation, can you do supervised learning? That's one of the problems that people who've been working in cosmology thought about for this kind of cosmology application. So that's the work of a group initially of people here at the Flatiron and in France at the Conservatoire Supérieur. So the idea was, once you know that you can reproduce the texture, can you use the representation of this to learn the cosmological parameters? Basically, the universe is defined by 6 or 8 parameters that people try to identify very precisely. Can you learn these parameters by getting the coefficient from this not learned neural network and do a linear regression? So what people showed, and there are several groups, one which was in John Hopkins, Xiao Cheng and Brice Mena, and one here with Michael Eichenberg, who's here, and the whole group, and Shirley Ho, is that basically you get results which are as good as the best deep network, which are learning everything in this case, which means you don't need to learn. Is that always the case? The answer is no. And now I'm going to show where it's not. Well, let me see how much time I have. I can skip quantum chemistry and finish in
5 minutes or 10?
You actually have as much. So it's really up to you. The slot is until 5, which is another half hour, but you can you can take another 10 minutes, another 20 as you
Okay,
prefer.
so I'm going to give you a
Brief idea of quantum chemistry, but then I would like to finish on image net,
because that's where the very difficult things are. So the problem of classification in this case, you want to maximize the probability of y. This is the base classifier given x, okay? And
the transform that I propose consists in splitting with a skip connection and splitting the different frequency band,
and then iterating on that, so reapplying a wavelet transform and the skip connection. And at the end, if these ones didn't go at the bottom of the tree, I'm going to do a pooling. I'm going to average so that everything is
at the final output. So this is my final operator, iteration of multi-scale decomposition, your nonlinearity, multi-scale your nonlinearity, average. That's a neural net. You didn't learn anything.
And then you do a linear classifier. How is this competitive with real, truly learned neural net? There is one reason
why this is not a crazy idea. Back to the symmetry. What I told you is that
a very important prior information is stability to deformation. If you take an image and you deform it, so it means translating each point of the image by an amount which depends upon position, you'll say that the deformation is small if this deformation change of metric is small. In other words, the Jacobian of tau has a largest eigenvalue, which is small in front of 1. So these are small deformation, and then we reach big deformation. Okay, there is one basic result, which says that
when you do this kind of transformation, you are regular, you almost linearize small deformations. Why? Because a small deformation is like a small dilation or a small compression. Now, that's exactly what a wavelet transform does. It looks at the object at different scale, and it exhibits the scale parameter. So what you can show is that if you take an image, you deform it. If you look at the output of your deep net built with your filters, if I look at the difference between a deformed image and an image, if you just look at the difference in L2, so Euclidean distance, it's going to be of the order of the size of the deformation. This is the metric of a deformation, which basically says how much a point has moved and how much the metric has been locally deformed. That's the standard metric of a deformation.
So that tells you that as long as you have a classification problem where the main issue is to identify deformations, you'll be good. If it's more complicated, it's less clear.
Quantum chemistry is an example where that works somewhat. So the problem of quantum chemistry is you have a particle. I'll go fast. You know the geometry, position of the atoms, the different type of atoms, and the problem is what is the energy of the molecules.
That's important if you want to make sure that your molecule is stable and if you want to analyze its properties. So, of course, you have numerical packages to do that, which basically computes the probability density of appearance of electrons, and then from there, compute the ground state energy. We'll do something much simpler.
We are first just going to look at the prior information we have on the problem.
Well, first thing, obviously, you need to label your nodes. So the let's say the energy doesn't depend upon your labeling, invariant to permutation. If you take your molecule, you rotate, translate it, the energy is not going to change, invariant to translation, rotation. If you slightly deform the molecule, the energy is going to progressively change. So you have a form of continuity to deformation. And you know that the forces are very strong at fine scale, less strong at larger scale, but not negligible. These are the Van der Waals forces in electromagnetic. So this is very simple, very similar to images. Same kind of properties that you get on image classification.
So there was whole group, and Michael, in fact, was at the École Normale Supérieure at that time, and who developed an algorithm without learning. So you basically take your molecule, just the position of the atoms, you send it into this network which emits local waves and take the modulus, so create patterns of interference. Then you pool everything, you have a small descriptor, and you do a linear classifier. And question, can from this you learn the energy of the quantum system? The interesting thing is that the answer is yes, but. Yes, it worked very well as the best deep network, but it worked very well only on simple databases. Simple databases means that the molecules were about 10 heavy atoms, not more complicated than that. And when you move to very complicated database, it looks like you need much more sophisticated algorithm. That's exactly what we see in images. If you want to classify digits, what is it to classify digits? Basically, you can go from a 5 to a 1 just by deforming the 5 into the 1. So you can view that as an identification of a deformation. Not quite, because an 8 has a hole, so you cannot go into a 1 because of topological obstruction, but this is the main ingredient. And indeed, if you go to MNIST, if you use the Lequin, Le Net, and the evolution afterward, or scattering, the errors are of the order of 0.3, 0.5%. Small errors of the same order of magnitude. If you want to classify textures, DeepNet doesn't bring anything. We've seen simple texture. If you want to classify really complicated problems, like ImageNet, which has 1,000 classes, complicated structures, 1 million images for training, it's much worse. You get about 50% error, which is not incredibly bad because you have 1,000 classes, but much worse, 5 times bigger than what a DeepNet does. So there, obviously, the question is, oops, let me come back to the question. What is long? What is the nature of what is being learned? The prior is not sufficient. So that was a work that was developed by Florentin Gut, who is here, and John Zafka. And the idea was to say, okay, let's keep what we know a priori. We know a priori that we want to split scale with these wavelet filters. They do the job. We know that the nonlinearity with a skip connection and a modulus seems to be do the job. But what we don't know is the model. Where is the model? The model is the connection here. Okay? So here we're going to learn, this is a 1-1 convolution operator. The only thing that we're going to learn is this 1-1 convolution operator. At the next scale, I propagate everything, and you learn the 1-1 convolution operators. Next scale, next scale. And then you do the linear classification. So now the learning, if you think of it in terms of physics, that would be the physical model, what defines the interactions between the coefficients here. Then you just split them with standard filters which define the scale. And they did a lot of work around that. And I'm going to show the results. So that's the architecture. The architecture is wavelet filters at all scales, different orientations, and the nonlinearity and the 1-1 convolutional filters, which is doing a dimension reduction also. Then you increase the dimension by splitting with multiple wavelets, and the 1-1 convolution, which reduce dimension, and so on. These are the number of channels. We picked exactly the same number of channels than a ResNet to have exactly the same kind of architecture. So as I said, if you don't learn these things, you just propagate the information. There is about 4 times bigger than a ResNet in the case of CIFAR, CFAR are small images of 32 by 32. ImageNet, which are bigger images, the ratio is almost a factor 5.
If now you learn the filters, you basically get the same precision.
So what that shows is that at least experimentally, everything is in these 1-1 convolutions. Everything is in these 1-1 convolution, which does the link. Of course, from a mathematical standpoint, is what is now the nature of this link? And that's what we don't understand. So the first idea that comes to mind is to say, oh, okay, let's look at these PJ. First layer, you can see something, and then it's a mess. You have the means of coefficient, and
It's at least we're not yet
able, but then it's a difficult thing. And I think that here we are lacking.
Somewhere we need to understand better. Now,
if I was to say what is there, I would say network. That's where you learn the pattern, the structures of the pattern.
Yes.
What are the number of degrees of freedom of the entire network?
About the same than the rest. Because the biggest number of parameters are in these 1-1. It looks, thanks for asking the question, because it looks like nothing, 1-1. But the 1-1 is because each layers are whole set of images to whole set of images, you have a huge matrix, this 1-1 condition. So there is no real reduction of parameters. Do we learn with less example and so on? We didn't. It's not an absolutely obvious because the number of parameters is still about the same. What we began to do is to try to reduce the number of parameters, and we can. But so what? You know, in terms of performance, the game here is not to beat deep networks. At this point, is really to understand. So it's more on trying to understand, and maybe once we'll learn, because the big number of parameters is here, we need basically to structure these 1-1. As long as we don't structure them, and that's what we began to try to do,
we won't beat them. Basically. So I'm going to finish on that.
So the conclusion, what is it?
The first one maybe is
we shouldn't forget, I think, that it's an unsolvable problem in general. So the reason why we can solve it
is that somewhere we are attacking very
structured problem. And people have a tendency when they do research in this field is to look for generic algorithms, generic optimization algorithms that are going to work and so on. And basically here the message is a bit different. The problem is not generic. Very well, it's the contrary I said at the beginning, sorry. It is generic in the sense that it applies to images, audio, and so on. But it's not going to apply to anything. So that means that audios, images, languages, they share structure. And in particular, the structure that they share is hierarchies. I mean, in the book, you have letters, words, paragraphs, chapters, and so on. The same in images. In audio signals and music, you have notes, you have measure, songs, musical phrase. All these are very structured. In all these problems, you have an axis which can be time, which can be space, on which you can do translation, convolution, a lot of structure. And that's what we're using through this convolution. So the way we use it is two ways. One, which I think is in some sense the most important, it's the fact that you have phenomena which separate, which are nearly independent within an image, or at least weakly correlated. Therefore, you can do some form of pooling and dimension reduction. So here we are really in the world of probabilities, of concentration. Then you have this second aspect, which is the aspect of symmetries. You have groups. Dilation scales is a group, translation is a group, rotation is a group, and then you want to understand how to move around these groups. And diffeomorphisms are even bigger group. And it's the two problems that you need to attack together. The other thing is this idea of phase. So I know that here at CCN, Eros Simoncelli did a lot of work in the past 20 years on that. And it's something that is very important, in particular in neurophysiology. Phase has to be looked at a bit independently from the modulus. Because when they are together, so you have real oscillating members, and you begin to do simple operations such as correlation, it's zero. You need to do the separation. The problem is that doing something naive like separating the phase from the modulus and processing the phase is totally unstable. So that's where these nonlinearities, such as ReLU in particular, have a very important role, and that's how you build these non-Gaussian models. And as I said, I think now a major challenge is to understand the relation between these filters and patterns, never. And there are all kinds of ideas around, but that's an open question, and how to mix that with what comes before. If you begin that way, same thing, you are dead. Why you are dead? Because if you try to build a model of this pattern, and then I deform it a little bit, you need to build a new model. And I deform it, you need to build a new model. So you first need to treat all the group actions that you know a priori, factorize them in some sense, and then at the end you get the essence and you can deal with patterns without too many patterns. But that's the open question. Thanks.
Thank you very much. Are there any questions? Also, are there any questions online?
Yes.
I have a relatively basic question, but I don't understand how you chose the parameters of the wavelets, that like the frequency and the yeah.
Yeah, that's an important thing. Basically, here we chose factor of 2. Why? Because one thing, okay, there's two levels of way of thinking. What kind of properties you'd like on your wave? You'd like something which is as local as possible, small, because you want to detect transient phenomena, edges, small, sharp variations. But you also want something which is well localized in the frequency domain in order to precondition your operators in particular. To do both, you need to have a function which is both regular and short support. Then to take a Gaussian, something modulated Gaussian, something that looks like it and so on, doesn't make huge differences. So here, what we imposed is to get the orthogonality property because it was then easier for the mathematics. Then the scale, which are powers of 2, computational, it's much easier because then you subsample by a factor of 2. Is there a gain to get a better wavelet and so on? That's something on which many people worked. At the time, it was to improve compression, that kind of application. It never got much better than the standard wave. I think that the real research issue is not so much there, but rather below how to use these coefficients to understand the nature of the signals. So basically, how to use them, you pick the one on the shelves, which have a good reputation, and you use them. Yes.
You said that the nonlinearity, you need the skip connections. Do you have an intuition about what kind of information you lose if you don't have the skip connections?
Phase. The phase, okay, so you can define the skip connection two ways. You may, you can take a ReLU of x and a ReLU of minus x. ReLU of x plus ReLU of minus x gives you back x. So you can put a ReLU, many ReLUs, and apparently you have no skip connection. But in the case where you really kill the phase with a modulus, the skip connection is what will allow you to still propagate the phase and allow you to identify the properties of the phase at the lower scale, for example, by correlating with the modulus or some other transformation. So, and it was very interesting because we did the classification without skip connection, everything with modulus. And we were stuck 10% above Resnet. And at the moment we put the skip connection, boom, we did a jump. And then, of course, you can make it, okay, what happened? And that was the fix. So it's not just for the pleasure of the map. It really makes a big, big difference. Same thing in the synthesis of textures. If you don't incorporate the phase, basically what's going to happen is that you have structures at different scale. If you don't realign them very precisely, you are not going to reconstruct a straight discontinuity. You are going to have what are called Gibbs phenomena because the phases are disaligned. Again, you need to propagate that phase to get that. So that's where these problems, in mathematics, these tools have been used until again the years 2000s, trying to get rid of the thing. The idea was you take your function, you represent it with coefficient. Then you just look at the amplitude of the coefficient and you'll have all the information. You didn't want to look at the thing. So it's really a bit of a disruptive idea to say, no, you still need to keep the phase. And that's another surprising idea that came from the deep net. And that was also an idea that were around in neural physiology. Yes?
Maybe also a basic question, but how easy or difficult is it to identify the correct symmetries of your problem that you're looking at? And is there a structured way to do so?
So that's another very good question on which we've been spending at least 5 years with quite a bit. So let me explain. There are some symmetries from a priori, but the basic symmetry is translation, rotation, at least 2 groups. And then obviously we couldn't get ImageNet perform. So the next question was, okay, we need to learn. Maybe we need to learn the groups. Maybe we need to learn these symmetries. And we tried. We tried by making learning convolutions across the channel. We tried all kinds of things. And it didn't really work. So the question I would translate in a different way. Do you need more symmetries than the basic symmetries, or is the rest about patterns? Patterns is structures which are not, you don't want to do groups of chairs and so on. I mean, it's not very, there is no reason why you have you imposing a group structures on such things. You could, but so right now, but I change my mind every 6 months. So if I give the talk in 6 months, I'll tell you probably something different. But right now, I have a tendency to say it's not about learning groups. There are the groups that use them because they're really important. And the rest, I would have tendency to think that it's more about understanding how to do a kind of memory, smart memory storage, which goes with it.
How did you encode the invariance with respect to the diffeomorphisms in the architecture?
Okay. You don't in the architecture because it would be very dangerous because you don't know in advance what is to what deformation you are invariant. For example, you take a 1, you deform it a bit, you have a 7, and you will make a mistake. So what you do is you rather try to linearize the deformation. In other words, a deformation will act as a linear operator in a space. And then the last layer is a linear operator. So the last layer can do a projection. And it's the last layer which is learning the environment. So that's one of the things. Translation, you may want to impose an environment, but not always. Sometimes, the face is well-centered. There is no reason to make something translation. So usually, you don't want to impose the environment. You just want to linearize the action of the group so that then if you want to kill it, you just do a linear projection. And that's why it's important to linearize the deformation so that then just a linear classifier can kill it.
So if I understood correctly, when you get to the last layer, you're hoping that the diffeomorphism doesn't cross your data point to the other side of the linear border.
Yes, and if it does, that means that it's a deformation that you need to keep, because then it's a very informative deformation. That's what goes from 1 to 7.
Right. Is there research on like this worst case diffeomorphisms, or maybe it's close to adversarial perturbations?
Yeah, in some sense, it would be a kind of adversarial example. It will depend very much on the problem. I don't have an answer. I don't know any studies specifically on that. Any other question?
Any more questions?
Yes.
So one question. So the way you presented this, it was kind of framed also in a bit of statistical theory viewpoint. I was just wondering, is there work that extends such methods to the sampling of or to learning of quantum field theories on a lattice from data, and to also efficiently sample configurations or things like that?
I would like. I mean, there is a path of research for me. It would be learning physics more. In other words, once you identify these potentials, how does it relate to the fundamental properties of the forces in the quantum field physics? These are very interesting questions. The fact that you have an underlying physics which is not too complicated in the sense that the number of forces, the number of parameters is not huge, tells you somewhere the problem is not too complicated. So you can grab it with these filters, which are a little bit brutal. But then going from there to the core physics is, for example, what they're trying to do when identifying the parameter in cosmology is yet another question. So it's an interesting topic. Thank you. Yes.
I was wondering how the memory you want to better understand or find is different from the memory or the idea of memory in deep networks, because I think in that setting, that's kind of a problem because you don't want to memorize your data, because then that leads to overfitting. And would a problem like that come up in your setting?
Yeah, and for me, there is no difference between this. Well, what we're doing is in some sense a simplified neural net. So I don't view it at all in a position, but rather trying to simplify a neural net and show the phenomena. So you're right about the fact that you can have an overfitting, and on problems such as n-lists, you can see that kind of phenomenon. Now, however, if you, at one point, there are structures, yeah, as you say, deep net, there is no question, they memorize. So it's important, obviously, to somewhere to memorize. And the question is, how do they memorize? What is the structure? It's obviously associative type memory. How does it go? In these cases, we know that the memory is not going to go into spatial filters because the spatial filters are wavelets, so they have nothing to do with whatever patterns it is. So the memory and these algorithms worked as well as deep net. So somewhere the memory was in the 1-1 convolution filters. But how did the memory was organized? Based on what principle? Is it something like a compressed sensing type algorithms where you have random filters and you look at the traits of your random filters? Is it, on the contrary, match filters? For example, do you expect that the filters look like the patterns or not at all? At least nobody really found a filter that looks like a chair in any way in these things. So, but is it rather random filters? Well, people tried to have totally random filters and it didn't work as well. So how is the memory captured? I think that's one of the major one question. Yes.
Perhaps a question about the quantum chemistry application. So, I mean, I guess one of the most popular one of the mostly used methods to do this is graph neural networks, but I guess they suffer from this issue that you have like only a local amount of messages that you can pass, so you cannot see very far in a sense. So I guess like van der Waals forces and things like that are not modeled very well, and in fact we had mostly the same problems that for QM9 this works rather well, but if you look at very large structural data sets, like for example OC20, where you have something like 200 atoms per cell, and also you have periodic boundary conditions, then it doesn't work very well. And so I was wondering whether there are approaches to combine these methods which do work well on short scales, like graph neural networks, which mostly capture like the covalent chemistry going on, with wavelet-based approaches in order to incorporate more like long-range interactions, electrostatics, these kinds of things. So if there's any communication between these parts of research.
That would be a very interesting work to do.
We have a summer school project, right? Otherwise, I mean,
these are very interesting questions. As you said, the graph methods are incredibly efficient with the local chemistry. You can get a lot of precision, unless indeed you go into strange phenomena like graphene, where there is very long range interactions that needs to be captured, or things like that. And there, yes, maybe these kind of methods are back in the game. But again, we would need still to capture it. Memory is also there in chemistry. I mean, there are groups of molecules which are associated to functions, and you'd better learn them, and any chemist know them. So the same, I think, that's what I liked about quantum chemistry, because it's a very well-posed problem, as I said, which is of similar nature as image processing, although the data is more complicated to get.
But that's a very interesting connection. I never thought of these two areas as being connected methodically, but I see the point. Definitely.
Yeah, and it's the only thing is that you need graphs to be very efficient, because the molecules don't have the good taste to live on a grid. Or you can do it brute force, which is the way we did, was to say, okay, we'll pick a high resolution grid, so the molecule lives on a 3D grid in high resolution. But that requires quite a lot of computation. And that was a bit of the limitation of, and Michael did a lot of things on that, and can comment on the suffering of doing 3D on fine-grained computation.
256 cube was a lot to put into GPUs. It works better now, but at the time it was a bit tough. I think we should wrap it up here, because our time slot is also ending. So let's thank Stefan again for this. I guess that concludes the